Hello there and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route toward rest. Tonight, we are drifting into one of those ideas that sounds simple at first, and then quietly grows so large that the mind has to sit down for a moment. We're talking about the distance between galaxies, those enormous stretches of space that separate one island of stars from another, and the strange truth that even when two galaxies look close together in a photograph, they may be so far apart that ordinary imagination has almost nothing useful to offer. And that is a slightly unfair thing about the universe, isn't it? It gives us numbers, it gives us measurements, it gives us light years, parsecs, redshifts, and careful diagrams made by people with very steady hands. But then it asks us to picture something like 2.5 million light years, or 50 million, or 1 billion, and our poor everyday brains, which are very good at finding the fridge in the dark and remembering where we left our slippers, simply look at those numbers and say, that seems excessive. Space is not just big in the way an ocean is big, or a desert is big, or the distance to the nearest shop feels big when it's raining and you forgot to buy milk. Space is big in a way that breaks the measuring tools we carry around in our heads. Before we drift too far from home, let me ask you something gentle. Where in the world are you listening from tonight? Are you tucked away in a quiet room, watching from a city full of lights, lying under a dark rural sky, or perhaps half listening while your thoughts are already loosening their grip on the day? And when you look up, if you can see the sky at all, does it feel near to you or impossibly distant? It is a funny little human habit, isn't it, to look at the night sky and feel that the stars are close, as if they have gathered above us like small lamps on a ceiling. But most of what we see is not close at all. Even the nearest stars are far beyond anything we can casually compare to a road, a flight, or a long walk with comfortable shoes. If you find this journey soothing, interesting, or just a gentle place to rest your thoughts for a while, I would be very grateful if you gave the video a like, maybe subscribed, and join this calm little corner of the universe again sometime. It helps the channel reach other people who might enjoy science that does not shout, rush, or throw too many flashing arrows at the screen. Around here we let the universe unfold at bedtime speed, which is probably the correct speed for a universe that has been around for nearly 14 billion years and has no urgent appointments as far as we know. So settle in, let your shoulders drop. Let the day move a little farther into the background. Tonight we are not trying to conquer cosmic distance. We are not trying to force the mind to hold numbers it was never built to hold. We are going to approach the distance between galaxies slowly, the way you might approach a dark shoreline at night, one careful step at a time. We will begin with familiar things, with Earth beneath us, with the moon, with the sun, with a little neighbourhood of planets that already feels enormous. Then gradually we will keep widening the view until our whole solar system becomes a dot. Then our star becomes one among hundreds of billions, and then even our galaxy, the Milky Way, becomes just one pale island in a wider sea of galaxies. The first thing to understand is that galaxies are not just bright smudges in space. They are massive systems containing stars, gas, dust, planets, black holes, dark matter, and long histories of collisions, births, deaths, and slow gravitational rearranging. Our own galaxy, the Milky Way, is thought to contain hundreds of billions of stars. Not hundreds, not thousands, hundreds of billions. If each star were a grain of sand, you would not be holding a pinch. You would be looking at beaches, dunes, bags, truckloads, and probably someone from health and safety asking why there is suddenly so much sand in the living room. And yet, the Milky Way is only one galaxy. There are many others. Some are spirals like ours with graceful arm curling around a bright centre. Some are elliptical, shaped more like soft glowing footballs or cloudy eggs. Some are irregular, messy, stretched, torn, or disturbed by past encounters. Galaxies come in different sizes and shapes, but almost all of them share one remarkable fact. They are separated by distances so large that the galaxies themselves, enormous as they are, become like tiny islands with vast dark water between them. This is where the imagination begins to wobble. Because when we look at pictures of galaxies, especially the beautiful images taken by telescopes like Hubble or James Webb, they often appear close together. You may see dozens of galaxies in one image scattered like fingerprints on black glass. Some overlap, some seem almost to touch. A small spiral may sit beside a golden elliptical. A faint little smudge may hang just below a bright disk. It looks crowded. It looks busy. It looks as though the universe has packed galaxies together like ornaments in a drawer. But those images are deceptive in a very understandable way. They flatten depth. They show us the sky as a two-dimensional picture, while the real universe has distance running away from us in every direction. Two galaxies that appear side by side may not be neighbours at all. One may be millions of light years closer than the other. They only look close because they happen to sit along a similar line of sight from Earth. It is a bit like looking across a field and seeing a bird on a fence post and a mountain behind it. In a photograph, they may seem close. In reality, the bird is having a very different day from the mountain. So what does it mean to say that a galaxy is millions of light years away? A light year is the distance light travels in 1 year. Light is fast, very fast. It moves at about 300,000 kilometers per second in a vacuum. That means in a single second, light could travel around Earth several times. In 1 minute, it covers about 18 million kilometers. In 1 day, it travels so far that ordinary road trip language starts to become useless. And in 1 year, light travels about 9.46 trillion kilometers. That number is already difficult. A trillion is not just a big million. It is a million millions. If you try to count to 1 trillion out loud, one number per second, without sleeping, eating, pausing, or becoming deeply unpopular with everyone nearby, it would take more than 30,000 years. So when we say 1 light year, we're already talking about a distance far beyond any direct human experience. And that is only 1 light year. The nearest major galaxy to the Milky Way, Andromeda, is about 2.5 million light years away. Let that sit beside you for a moment. Not because you need to fully picture it. You probably cannot, and that is not a failure. Nobody really can. Andromeda is our large galactic neighbour. In cosmic terms, it is nearby. It is part of our local collection of galaxies. It is close enough that, under dark skies, some people can see it with the naked eye as a faint, soft patch. And yet the light from Andromeda has been travelling for about 2.5 million years before it reaches your eye. When that light began its journey, early humans on Earth were living in a world of stone tools, changing climates, and animals that would have looked both familiar and strange. The light crossed intergalactic space for longer than all recorded human history, longer than agriculture, longer than cities, longer than writing, longer than every empire, language shift, invention, argument, lullaby, recipe, and slightly overconfident weather forecast humans have ever produced. And Andromeda is considered nearby. That is the part that quietly turns the room upside down. The Milky Way and Andromeda are separated by a distance that, on human scales, is absurd. But on galactic scales, they are companions. They are gravitationally linked. In fact, they are moving toward each other and are expected to merge billions of years from now. That sounds dramatic, and it is, but not in the way a car crash is dramatic. Galaxies are mostly empty space, so when galaxies merge, stars usually do not slam into each other. They pass through the combined system like tiny sparks moving through a huge dark hall. Gravity rearranges everything. Gas clouds collide and can trigger new star formation. The galaxies stretch, bend, and eventually settle into a new form. It is a slow, enormous reshaping, not a sudden smash. If the universe had a patience competition, galactic mergers would be strong contenders. Still, before we get carried into the distant future, it helps to return to the present distance. 2.5 million light years. You might try to shrink it down. Suppose the Sun were the size of a grain of sand. Even then, the distance to the nearest stars would be hard to place comfortably in a room. Now imagine trying to include the entire Milky Way, which is about 100,000 light-years across, and then place Andromeda 2.5 million light-years away. If the Milky Way were a small coin, Andromeda would be another coin many coin widths away across the table, and the space between them would not be filled with much that shines. A few small dwarf galaxies, some thin gas, stray stars, particles, radiation, dark matter, and the long quiet stretch of intergalactic space. Not empty in an absolute sense, but empty enough that the word empty begins to feel reasonable. The trouble with scale models is that they often collapse under cosmic distances. Make the planet small enough to fit in a classroom, and the nearest stars end up far away across the country. Make the Milky Way small enough to hold in your hand, and the distances between galaxies still demand a bigger room than most of us have available. The universe keeps refusing to be conveniently demonstrated. It is like trying to explain an ocean using a teaspoon. The teaspoon is not wrong, it is just having a difficult assignment. One of the gentlest ways to think about the distance between galaxies is not as distance in kilometers, but as time for light. When we say Andromeda is 2.5 million light-years away, we're also saying we see it as it was 2.5 million years ago. Every telescope is a time machine in this limited but very real sense. It does not carry us backward physically. It does not let us step into the past wearing suspiciously modern shoes, but it shows us light that left long ago. The farther away we look, the older the light. A galaxy 100 million light-years away is seen as it was when dinosaurs still walked Earth. A galaxy billions of light-years away is seen as it was before Earth had complex life, before our planet looked anything like the familiar world we know. That means the distance between galaxies is also a distance between moments. The universe is not displayed to us all at once in a single, universal now. It arrives by light, and light takes time. The night sky is a mixture of different ages. The moon is a little over 1 light-second away. The sun is about 8 light-minutes away. Nearby stars are years away by light. Nearby galaxies are millions of years away. Distant galaxies are billions. Looking outward is looking backward, not because the universe is trying to be mysterious for dramatic effect, although it certainly succeeds, but because information has a speed limit. This gives cosmic distance a strange emotional texture. Andromeda is not just far away. It is old news arriving beautifully late. A distant galaxy is not just a place. It is a message sent across a depth of time so large that Earth may have changed completely while the message was travelling. By the time some light reaches us, the stars that emitted it may have aged, exploded, or drifted into new arrangements. The galaxy may have merged with another. Entire generations of stars may have lived and died. We see what arrived, not necessarily what is happening there now. And yet, this delayed view is not a problem for astronomy. It is one of its greatest gifts. Because light carries information, astronomers can use these long-travelling messages to reconstruct cosmic history. They can study young galaxies in the early universe, compare them with older galaxies nearby, and piece together how galaxies form and evolve. The distance between galaxies, enormous as it is, becomes a kind of archive. The universe stores its past in travelling light. Of course, if we're going to understand why these distances feel so impossible, we need to remember how small our normal lives are by comparison. Most of us experience distance through time spent moving. The shop is 10 minutes away. A nearby city is an hour. Another country might be a flight of several hours, plus the ritual of airport security, which somehow bends time in its own special way. The Moon took Apollo astronauts about 3 days to reach. Mars, depending on where it is in its orbit, takes spacecraft many months. Pluto took New Horizons more than 9 years to fly past. These are already huge achievements. They are not small distances. They are heroic distances for machines built on one rocky planet by a species that still occasionally loses its keys. But the nearest star beyond the Sun is over 4 light-years away. With current spacecraft speeds, reaching even that neighbourhood would take tens of thousands of years, and that is only the next star system, still inside our galaxy. To cross the Milky Way itself would require a journey of about 100,000 years at light speed, which no spacecraft can do. To reach Andromeda at light speed would take 2.5 million years. At any realistic speed we can currently build, the travel time becomes so long that it stops sounding like a trip and starts sounding like geology with a destination. That is why the distance between galaxies is not just hard to imagine, it changes the meaning of travel. We're used to distance being something effort can overcome. Walk longer, drive faster, fly higher, build better engines. But intergalactic distance is so large that even light, the fastest thing in the universe, takes millions or billions of years to cross it. At that scale, speed itself feels humbled. Light does not seem fast anymore, it seems patient. There is something calming about that if we let it be calming. The universe is not arranged around our urgency. Galaxies do not hurry toward one another because we're curious. Light does not arrive sooner because we would like a clearer picture. Space is wide, and it does not apologize for being wide. It simply is. We live inside that width, on a planet that is both incredibly small and, for us, completely full. Full of weather, rooms, faces, meals, traffic lights, trees, messages, sleep, small worries, and small joys that do not become less real because galaxies are far apart. In fact, the impossible scale of galactic distance can make the ordinary world feel more precious, not less. Your room is small compared with the Milky Way, but it is where you can rest. Your town is tiny compared with a galaxy cluster, but it is where morning happens to you. Your life is brief compared with the travel time of light between galaxies, but it is the only place from which you can wonder about any of this. The universe may be vast beyond easy thought, but the act of thinking about it happens somewhere very specific. It happens here, in a human mind, perhaps late in the evening, perhaps with tired eyes, perhaps under a blanket, while the galaxies continue their slow motion far beyond the roof. As we move deeper into this topic, we will keep returning to that balance, the enormous and the personal. For now, it is enough to begin with this simple, unsettling idea. The Milky Way is not alone, but it is also not crowded in any everyday sense. Around it lies a deep region of space, thinly filled, faintly threaded, and crossed by light that has been travelling longer than human beings have been human in the way we recognise. Somewhere beyond that dark gulf, Andromeda shines with its own hundreds of billions of stars. It is our neighbour, our future companion, and yet it is so far away that its light had already been travelling toward us before our ancestors had stories, cities, or names for the stars. So when you next see a galaxy in a photograph, small and bright against blackness, try not to think of it as a nearby object pasted onto the sky. Think of it as a continent of stars seen across a distance so large that even light arrives ancient. Think of the space around it not as a blank background, but as part of the story. The darkness between galaxies is not just empty scenery. It is the scale of the universe made visible, and once we begin to notice that darkness, once we stop looking only at the glowing islands and start paying attention to the distance between them, the universe becomes even larger, quieter, and far more interesting than it first appeared. Somewhere after the first shock of cosmic scale, the mind usually reaches for a very reasonable question. All right, the universe is enormous. Galaxies are far apart and light has to travel for ages just to bring us a picture. But how far away is the nearest galaxy really? Not the nearest star, not the nearest planet, not the moon, which already feels like a proper outing. The nearest galaxy, the closest separate island of stars beyond the one we live in. Surely that should be a little easier to imagine. Surely our nearest galactic neighbour must be just over the fence, cosmically speaking, perhaps waving politely from the next dark patch of space. And in one sense, yes, it is nearby. is. In another sense, it is so far away that the word nearby begins to look a little embarrassed. The first funny thing about asking for the nearest galaxy is that we have to remember where we are. We're not outside the Milky Way, looking back at it from a safe distance like someone admiring a house from across the street. We're inside it. We live in one of its spiral arms, on a small rocky planet orbiting an ordinary star, surrounded by other stars that all belong to the same enormous system. So when we ask, where is the nearest galaxy, we're really asking, what is the nearest galaxy outside our own? It is a bit like standing in a city and asking where the nearest city is. The answer depends on whether you count the one under your feet. The Milky Way is our home galaxy, and it is not a small thing. It is a broad rotating disk of stars, gas, dust, dark matter, and old stellar populations, with a central bulge and long spiral arms winding outward. It is about 100,000 light-years across, depending on exactly how you define its edges, which are not marked with a neat little sign saying, "You're now leaving the Milky Way. Please drive carefully." Galaxies do not have hard borders like countries on a map. Their stars thin out, their gas fades, their dark matter halos stretch much farther than the visible glow. The edge is not a wall. It is more like the gradual end of a crowd, where people become fewer and fewer until you realize you're mostly standing alone. Around the Milky Way are smaller galaxies, dwarf companions that orbit or interact with it. These are not giant spirals like the Milky Way. They are smaller systems, some with billions of stars, some with far fewer, and some so faint and spread out that finding them is a bit like trying to spot spilled sugar on a patterned rug. A few of these dwarf galaxies are so close and so tangled with the Milky Way's gravity that they are being pulled apart, stretched into streams, and slowly absorbed. So the nearest galaxy is not necessarily the one most people imagine. It is not always the grand Andromeda galaxy, that famous spiral often described as our nearest galactic neighbour. Andromeda is the nearest major galaxy, yes, but the truly nearest galaxies are smaller, dimmer, and much more entangled with our own. One of the closest known is the Sagittarius dwarf spheroidal galaxy. It lies tens of thousands of light-years away from us, close enough in galactic terms that it is not just a neighbour, but more like a guest who has wandered into the hallway and is now being slowly taken apart by the furniture. The Milky Way's gravity is stripping stars from it, pulling them into long streams that wrap around our galaxy. This is not a neat, peaceful orbit in the way a planet orbits the Sun. It is a slow gravitational unravelling. The smaller galaxy is being stretched, tugged, and blended into the larger one. In the distant future, much of it may simply become part of the Milky Way's halo, its stars folded into our galaxy's extended outskirts, like old memories added to a larger story. That already complicates the question, doesn't it? If a galaxy is being torn apart by the Milky Way, still passing through or around it, still holding some identity of its own, but also slowly dissolving into us, where exactly is the nearest separate galaxy? Space rarely offers tidy labels. It prefers gradients, overlaps, and situations that make textbook diagrams quietly sweat. Then there are the Magellanic Clouds, two of the most famous satellite galaxies of the Milky Way. The Large Magellanic Cloud is about 160,000 light-years away, give or take the usual astronomical carefulness. The Small Magellanic Cloud is farther, around 200,000 light-years away. If you live in the southern hemisphere or far enough south, these galaxies can be seen with the naked eye under dark skies as soft cloudy patches. They do not look like the grand spiral photographs you may have seen online. To the unaided eye, they look gentle, pale, and almost modest, which is a little unfair because the Large Magellanic Cloud contains billions of stars. Imagine being made of billions of suns and still appearing to humans as a faint smudge. The universe has a way of keeping egos in check. The Large Magellanic Cloud is especially interesting because it is both near and large enough to study in great detail. It has star-forming regions, old star clusters, gas clouds, and one of the most active stellar nurseries in our cosmic neighbourhood, the Tarantula Nebula. That name does sound as if astronomy briefly handed the naming duties to someone who had just looked under a bed, but it is a spectacular region where massive stars are being born. Even at a distance of roughly 160,000 light-years, astronomers can study individual stars inside the Large Magellanic Cloud. That is remarkable. We are not just seeing a blur, we are resolving parts of another galaxy. But pause for a moment on that number. 160,000 light-years. This is not the distance to the nearest major galaxy. This is the distance to a nearby satellite galaxy, a companion of the Milky Way, something close enough to be part of our local galactic family. Light leaving the Large Magellanic Cloud tonight will reach Earth around 160,000 years from now. That means if someone there had a lamp bright enough to be seen across intergalactic space, which would be a very ambitious lamp, and probably terrible for their electricity bill, we would not see tonight's flash until a time when everything familiar about our civilization had either changed beyond recognition or disappeared into history. When the light we see from the Large Magellanic Cloud began travelling toward us, modern humans existed, but the world was a very different place. There were no cities, no farms, no writing, no telescopes, no names for galaxies, no late-night videos about astronomy helping people fall asleep. The light crossed space while ice ages came and went, while human groups moved across landscapes, while languages emerged and vanished, while every known civilization had not yet begun. It arrived only now carrying an image of a nearby galaxy, as it was before the entire human story we usually call history had even opened its first page. And that is the close one. This is why cosmic nearness is such a strange concept. The Large Magellanic Cloud is one of our nearest galactic neighbours, and yet its light has travelled longer than any city has existed. The Sagittarius dwarf is closer, but it is faint, disrupted, and deeply bound up with the Milky Way's own structure. The small Magellanic Cloud is a little farther than the large one, but still nearby in the grand scheme. These galaxies are our local companions, our satellite systems, our immediate surroundings beyond the main body of the Milky Way. But none of them are reachable in any familiar sense. They're close only because the universe has set the comparison scale to something wildly unreasonable. Think about travel for a moment. Light from the moon takes a little more than 1 second to reach us. Sunlight takes about 8 minutes. These already make the solar system feel spacious. If the sun vanished right now, which to be clear it is not planning to do, we would not know for about 8 minutes. The sunlight already on its way would keep arriving, cheerful and unaware of the imaginary disaster behind it. Mars, depending on where it is in its orbit, may be several light minutes away. The outer planets are light hours away. Pluto is usually several light hours away. These distances are large enough that spacecraft communication has noticeable delays. You cannot joystick a rover on Mars in real time like a remote-controlled car. You send instructions, wait, and hope it does not choose that exact moment to become intimate with a rock. Now step beyond the solar system. The nearest star system, Alpha Centauri, is a little over 4 light-years away. 4 light-years. That means light, moving at the fastest speed anything can move through space, still needs more than 4 years to get there. A spacecraft like Voyager, moving at a tremendous speed by human standards, would take tens of thousands of years to cover that distance. And Alpha Centauri is not in another galaxy. It is one of our neighbours inside the Milky Way. It is practically down the cosmic lane, and yet with our current technology, it is beyond any human lifetime journey. Now compare that to the Large Magellanic Cloud, about 160,000 light-years away. That is roughly 40,000 times farther than Alpha Centauri. Then compare it to Andromeda, about 2.5 million light-years away. Andromeda is more than 15 times farther than the Large Magellanic Cloud, and more than 500,000 times farther than Alpha Centauri. The numbers stack up so quickly that they lose their grip on normal understanding. They become not just big, but slippery. Andromeda is the galaxy many people first think of when they hear nearest galaxy, because it is the nearest large spiral galaxy to the Milky Way and the most famous outside our own. It is also visible to the naked eye from dark locations in the northern hemisphere. Under good conditions, it appears as a faint elongated glow in the constellation Andromeda. It is not flashy. It does not announce itself with dramatic music. It simply waits there, soft and pale, carrying the combined light of around 1 trillion stars depending on the estimate, and looking to human eyes like a little breath of mist. There is something wonderfully humbling about that. The largest and nearest major galaxy to us, a system wider and perhaps more star-rich than the Milky Way, appears without a telescope as a faint smudge. If you did not know what you were looking at, you might miss it. You might glance over it while searching for a brighter star. Yet that smudge is an entire galaxy, a vast rotating system with spiral structure, star clusters, dust lanes, satellite galaxies of its own, and a central supermassive black hole. Its light has been travelling for about 2.5 million years. When it left Andromeda, our ancestors on Earth were not astronomers with charts and lenses. They were early humans and human relatives moving through changing landscapes, making tools, surviving weather, and living lives that have left only scattered traces. So when someone points to Andromeda and says, "That is our nearest large galactic neighbour," it is true, but the statement hides a distance so deep that the light itself is ancient by the time it arrives. Imagine sending a message and waiting 2.5 million years for a reply. Even the most patient person would begin to suspect they had been left unread. The difference between satellite galaxies and major galaxies also helps us understand how galactic neighbourhoods work. The Milky Way is not alone. It is surrounded by smaller galaxies, many of which are gravitationally bound to it. These smaller galaxies orbit, fall in, get stretched, and sometimes merge with the Milky Way over long periods. In that sense, our galaxy is not a sealed object floating in isolation. It is part of a system, a larger gravitational environment. The local group, as astronomers call it, includes the Milky Way, Andromeda, the Triangulum Galaxy, and many smaller dwarf galaxies. It is our wider cosmic neighbourhood, not a neighbourhood where you can borrow a ladder or complain about someone's hedge, but still a neighbourhood. The local group spans millions of light years. Its largest members are the Milky Way and Andromeda, with Triangulum as another significant spiral galaxy. Around them are numerous dwarf galaxies, some bright enough to be well known, others faint enough that they have only been discovered through careful surveys. These small galaxies matter because they tell us how bigger galaxies grow. Large galaxies like ours did not simply appear fully formed. Over cosmic time, they gathered material, merged with smaller systems, absorbed gas, formed stars, and changed shape. The faint dwarf galaxies nearby are not just decorations around the Milky Way. They are evidence of that long process still happening. In a way, the nearest galaxies are both neighbours and leftovers. They are independent systems, but they are also part of the Milky Way's ongoing story. Some may survive for billions of years, others are being torn apart. Their stars may eventually become mixed into the halo of our own galaxy, so far from the central disk that future observers might never know which small galaxy they originally belonged to. The border between one galaxy and another can blur over time. Gravity is not sentimental about keeping things in separate boxes. This is important because when we imagine galaxies, we often picture them as clean, separate islands floating in black space, and sometimes that is a useful picture. But close to a large galaxy, the picture becomes messier. Dwarf galaxies orbit, stellar streams arc through the halo, gas can be pulled away, dark matter halos overlap, some stars may be kicked out into intergalactic space. The nearest galaxy may not be a crisp object sitting politely at a measurable distance. It may be a battered companion already being reshaped by our own galaxy's gravity. Still, for the human imagination, the Magellanic Clouds and Andromeda give us useful stepping stones. They allow us to feel the ladder of galactic distance, First, there are the disrupted dwarfs, close but faint and tangled with the Milky Way. Then the Magellanic Clouds, visible satellite galaxies, close enough for detailed study, but still so far that their light began its journey before civilization. Then Andromeda, the great spiral neighbour, visible as a smudge, close in the cosmic sense but millions of light-years away. Each step outward is not merely farther, it changes the kind of thinking required. A helpful comparison is to imagine the Milky Way as a city at night. The satellite galaxies are like small towns and settlements scattered around it, some close, some farther out, some being absorbed into the growing suburbs. Andromeda is another great city far across a dark plain. You can see its glow on the horizon, but the horizon is not a few miles away. It is so far away that the light from its skyline started toward you before your species had finished becoming itself. That image is not perfect, because galaxies are not cities, and intergalactic space is not a plane, but it gives the mind something to hold without forcing it to balance a tower of zeros. Another way to think about it is through the night sky itself. If you can see the Milky Way as a pale band overhead, you're looking into the disk of our own galaxy. Those stars, that hazy glow, that spilled-looking light across the darkness, all belong to the same large system we inhabit. If you can see the Magellanic Clouds from the southern sky, you're looking at small galaxies nearby. If you can see Andromeda from the northern sky, you are looking beyond the Milky Way to a major galaxy far outside it. With no engine, no spacecraft, no movement at all, your eyes can cross distances that no human body could ever travel. Vision is the only part of us that regularly makes intergalactic journeys before breakfast. Yet even vision has limits. Most galaxies are too faint to see without telescopes. The universe contains countless galaxies beyond our naked eye reach, some millions, some billions of light-years away. Telescopes gather more light than our eyes can, and long exposures allow faint objects to emerge. This is why deep-field images are so powerful. A patch of sky that appears empty can, with enough observing time, reveal thousands of galaxies. Not stars, galaxies, each one with billions of stars, each one separated from the others by distances that turn even Andromeda's 2.5 million light-years into a local stroll. That is where the nearest galaxy becomes more than a trivia answer. It becomes the first clue to a larger truth. If the closest galaxies are already this far, then the universe is not merely sprinkled with galaxies like raisins in a cake. It is structured on scales so large that even galaxy groups are small features. Our nearest companions teach us what distance means at the beginning of intergalactic space. They show us that the darkness between galaxies is not an empty mistake in the picture. It is the dominant part of the picture. And maybe that is why this question feels so peaceful after the initial shock wears off. How far is the nearest galaxy really? Far enough that light becomes a historian. Far enough that human time seems brief. Far enough that even our nearest neighbours are messages from deep history. But also close enough to see, study and include in our understanding of home. The Milky Way is not isolated. It has companions. It has a neighbourhood. It has smaller galaxies moving around it and a larger future waiting with Andromeda somewhere ahead. We are tiny, yes, but not disconnected. We are part of a local cosmic arrangement, a gravitational family spread across millions of light-years. So the nearest galaxy is not one simple answer. It depends what we mean by galaxy, by nearest, by separate, by major, by visible, by neighbour. The Sagittarius dwarf and other nearby dwarf systems remind us that galaxies can be faint, disrupted, and close enough to be slowly swallowed. The Large Magellanic Cloud reminds us that a nearby satellite can still be so distant that its light began travelling before recorded history existed. Not far beyond the edge of ordinary imagination, there is a dark stretch of space that sits between our galaxy and Andromeda. It is tempting to picture it as empty, because that is what it seems to be when we look up. The stars are here, The galaxy is there, and between them there must simply be nothing. A clean black gap, the quiet space between two lamps in a dark room. But the universe rarely gives us anything that simple. Even its emptiness has texture. Even its silence has structure. And the space between the Milky Way and Andromeda, that vast gulf of roughly 2.5 million light-years, is not really a blank space at all. It is more like an ocean so wide and so thin that a ship could sail through it for ages and almost never meet a wave. The word ocean is useful here, but only if we are careful with it. A real ocean on Earth is dense, moving, salty, noisy, and full of things that bite, glow, drift, swim, or look like someone designed them during a fever dream. The ocean between galaxies is nothing like that. It is not full in any ordinary sense. It is not blue. It does not splash. You would not hear it moving against a shore. It is made of rare atoms, faint radiation, dark matter, scattered stars, ghostly gas, and the enormous reach of gravity. In most directions, it is thinner than the best vacuum humans can make in a laboratory, and yet, compared with perfect nothingness, it is busy. It has history. It has motion. It has invisible borders, overlapping halos, an ancient material that has been pushed out of galaxies by exploding stars and pulled around by gravity for billions of years. If you were somehow placed halfway between the Milky Way and Andromeda, and let us assume you had a very reliable spacesuit, excellent snacks, and no urgent plans for the next few million years, the view would be strange. The Milky Way would not look like the band of light we see from Earth. From outside, it would reveal itself as a broad spiral system, a pale disk with arms, dust lanes, a bright centre, and a faint halo surrounding it. Andromeda would shine in another direction, larger in mass and spread, also spiral, also glowing with hundreds of billions of stars. Between them, the sky would not be crowded with nearby suns. There might be a few stars scattered in the darkness, perhaps stars thrown out from galaxies long ago, or members of small dwarf systems moving through the local group. But mostly, you would be looking across a blackness so wide that even galaxies would appear as distant objects, not places you could simply drift toward by being patient for a weekend. This is one of the first things to understand about intergalactic space. It is not empty because there is absolutely nothing there. It is empty because the meaningful things are spread so far apart. A single atom in a room is almost nothing. A single atom in a cubic meter of intergalactic space is also almost nothing. But the scale is so vast that all those almost nothings add up into something real. Thin gas can still form halos. Faint plasma can still absorb light. Dark matter can still shape motion. Gravity can still connect objects across distances that make a human lifetime feel like the blink of a tired eye. Around the Milky Way, the visible disk of stars is only part of the galaxy. We tend to imagine our galaxy as the bright spiral, because bright things are easier to love and easier to draw. But galaxies have halos too. A halo is a vast, roughly spherical region surrounding the brighter disk. It can contain old stars, globular clusters, gas, and large amounts of dark matter. The halo does not stop neatly at the edge of the visible galaxy. It fades outward, thinning and weakening, but still influencing what moves nearby. And Andromeda has a halo as well, one that astronomers have studied by looking at the light of faraway quasars behind it. As that quasar light passes through Andromeda's faint surrounding gas, some wavelengths are absorbed, leaving clues in the light. It is a little like detecting an invisible fog by noticing that a lamp behind it has changed colour ever so slightly. What they found makes the space between our galaxies feel less empty than it first appears. Andromeda's gaseous halo stretches more than 1 million light-years from the galaxy, about halfway toward the Milky Way, and in some directions even farther. That means the outer atmosphere of Andromeda, if we can use the word atmosphere very loosely and carefully, reaches far beyond the bright disk we see in telescope images. It is not a sharp bubble, not a soap film edge, not a glowing shell. It is diffuse plasma, spread so thin that if you passed through it, you would not notice a breeze. But with sensitive instruments and careful measurements, astronomers can see its imprint. The galaxy is larger than its starlight. That phrase matters. A galaxy is larger than its starlight. The Milky Way is larger than the band we see. Andromeda is larger than its bright spiral. Their visible disks are like the lanterns of much broader systems. Around them are faint envelopes of gas and dark matter, extending outward into the space between. So when we imagine the gulf between the Milky Way and Andromeda as empty water between two islands, we should also imagine that each island has a great unseen reef, a wide, shallow region spreading outward below the surface. The islands may look separate from above, but their hidden structures may reach toward one another across the dark. And this gives us a quieter, more complicated view of galactic distance. The centre of Andromeda is roughly 2.5 million light-years away from us, but its outer halo reaches inward, toward our own region of space. The Milky Way has its own extended halo as well. These halos do not behave like solid objects. They do not clink together like glasses at dinner. They can overlap, blend, and interact very gently, in ways that are difficult to picture because the material is so thin. But the idea is still astonishing. The bright starry parts of the Milky Way and Andromeda remain enormously far apart, and yet their wider environments may already be reaching toward each other. If that sounds like a collision happening in slow motion, that is not entirely wrong, but we should be careful not to make it too dramatic. When people hear that the Milky Way and Andromeda may one day merge, it is easy to imagine a catastrophic crash, stars exploding into one another, planets knocked around like billiard balls, cosmic traffic insurance forms being filled out by extremely stressed astronomers. But galaxies are mostly space. Stars are tiny compared with the distances between them. Even inside a galaxy, where stars are much closer together than they are between galaxies, the gaps are enormous. When galaxies merge, the stars usually pass by one another at great distances. The real drama is gravitational. Orbits change, gas clouds collide, star formation can be triggered. Spiral arms distort. Tails and streams may form. Over very long periods, the galaxies reshape into something new. So the empty ocean between the Milky Way and Andromeda is not simply a waiting room for a future impact. It is already part of the relationship between the two galaxies. Gravity crosses it. Gas may trace it. Dwarf galaxies move through it. Dark matter structures help define it. Light travels through it, carrying old images from one galaxy to the other. If there were observers in Andromeda, looking back toward us with powerful telescopes, they would see the Milky Way as it was about 2.5 million years ago. Earth would not show them cities, radio towers, satellites, or anyone arguing gently with a fitted sheet while making the bed. They would see an ancient Earth, long before recorded history, because our present has not had enough time to reach them. This is where distance becomes almost personal. The space between the Milky Way and Andromeda is not just a gap in location, it is a delay in knowing. We cannot see Andromeda as it is right now if right now even has a simple meaning across such distances. We see it as it was when its light left, and any light leaving us tonight will not arrive at Andromeda until millions of years have passed. In a universe like this, even neighbours know each other slowly. There is no instant glance across the fence. There is only light travelling, patient and silent, through a dark ocean. Imagine sending a postcard across that gulf. Not a radio signal, not a laser pulse, just a friendly little postcard that says, "Hello from the Milky Way, weather mixed, humans still confused but trying." Even if it travelled at the speed of light, the message would need about 2.5 million years to reach Andromeda. A reply would take another 2.5 million years to return. A 5 million year conversation for one exchange. By the time the answer came back, continents would have shifted slightly, species might have changed, and whatever counted as a normal Tuesday would be very different. Cosmic communication is not impossible in principle, but it does require a level of patience usually not found in group chats. The emptiness between galaxies also tells us something important about why galaxies appear as separate objects at all. Stars inside a galaxy are bound together by gravity. Gas, dust, stars, and dark matter share a common gravitational system. But between galaxies, the density drops dramatically. The pull of one system fades, the pull of another grows, and large regions exist where matter is sparse and spread out. This sparse space allows galaxies to keep their identities for billions of years. If the universe were packed evenly with stars everywhere, galaxies would not stand out as islands. The darkness between them is part of what makes them visible as galaxies. The gap defines the object. There is a strange comfort in that. The space between things is not always empty in a meaningless way. Sometimes it is what lets things have shape. A pause in music lets the next note feel clear. The dark between stars lets constellations appear. The gap between galaxies lets us see them as separate worlds of stars. Without the empty ocean, the islands would vanish into one continuous glare. The universe is not only made of what shines, it is also made of the distances that allow shining things to be noticed. Of course, if we could travel through that ocean, we would not experience it as a peaceful cruise. We would experience almost nothing at all, for a very, very long time. Suppose a spacecraft left the Milky Way heading toward Andromeda. First, it would have to cross the outer regions of our own galaxy, passing beyond the familiar disk, beyond most of the visible stars, into the halo. The star density would thin. The bright band of the Milky Way would change behind it, becoming less like a sky and more like a shape. The sun would become one faint point among many, then eventually indistinguishable without precise instruments. The spacecraft would enter a region where nearby stars were rare, and where the main thing surrounding it were thin gas, particles, radiation, and darkness. Then the long crossing would begin. At any speed we can currently imagine building, the trip would be absurdly long. Even at a significant fraction of the speed of light, it would take millions of years. At ordinary spacecraft speeds, the times become so large they are no longer really travel times in a human sense. They are spans of planetary evolution. Civilizations could rise and fall many times over before the ship crossed a meaningful fraction of the distance. A journey to Andromeda would not be a voyage for a crew in the usual way. It would be a project for descendants, machines, or something stranger. Something able to treat deep time as casually as we treat a long train ride, and honestly, many of us are barely patient enough for the train ride. Yet light makes the trip constantly. Every second, light from Andromeda enters the Milky Way. Every second, light from the Milky Way travels outward toward Andromeda. Photons cross the gulf in both directions, carrying information about stars, dust, gas, and motion. We cannot ride with them, but we can receive them. Astronomy is built on this strange generosity. The universe sends messages whether or not it knows anyone is listening. We build instruments, collect the light, separate it into wavelengths, study tiny shifts and missing pieces, and slowly turn those arriving photons into a story. Some of those photons pass through the diffuse material between galaxies. That material can be so thin that it barely announces itself, but barely is enough. If light from a distant quasar passes through a halo of gas before reaching us, atoms and ions in that gas can absorb specific wavelengths. Those missing wavelengths are fingerprints. They reveal what elements are present, how the gas is moving, and sometimes how hot or ionized it is. This is one of the cleverest things about astronomy. We cannot scoop up the gas between galaxies with a bucket. We cannot sail out and sample it like seawater. But we can let background light pass through it and read the changes, the way you might know a person walked through a room because the dust moved in a beam of sunlight. The gas in galactic halos is also connected to the life cycle of galaxies. Stars form from gas. Massive stars explode and throw material outward. Supernovae enrich space with heavier elements, the ingredients needed for planets, rocks, and living chemistry. some of that material escapes into the halo. Some may eventually fall back in. Galaxies breathe, in a sense, not like animals, but through the movement of gas into and out of their disks. The space around a galaxy is not a dead border. It is part of a circulation system. Gas can be accreted, expelled, heated, cooled, stripped and recycled. The empty ocean is thin, but it is not irrelevant. Between the Milky Way and Andromeda, this means the darkness is tied to the past lives of stars. Some of the atoms drifting in those faint halos may have been forged in stellar interiors or thrown out by ancient explosions. They may have belonged to gas clouds, stars, or smaller galaxies before being scattered into the wider local group. The material is rare, but it has a history. It is not just leftover space. It is the dust and breath of galactic evolution spread almost beyond recognition. There may also be stars in the space between galaxies, though they are very sparse. Some stars can be flung out of galaxies by gravitational interactions. Others may belong to faint stellar streams, the remains of dwarf galaxies pulled apart by larger ones. In galaxy clusters, where many galaxies interact, intra-cluster stars can drift between the main galaxies in large numbers. In our local group, the space is much less crowded, but it is still not impossible for stars to exist outside the main disks. A lonely star between the Milky Way and Andromeda would have a view unlike anything from Earth. Its night sky might contain two great spiral galaxies in different directions, each one a distant home of countless suns. If it had planets, and if some unlikely observer stood on one, their idea of the galaxy might be split between two glowing shapes rather than one band overhead. That is a lovely thought, but also a reminder of how rare such places would be. Most of the crossing is not filled with stars, it is filled with distance. Distance is so large that even the galaxies at either end remain remote for most of the journey. If the Milky Way and Andromeda are like two cities, then the region between them is not a countryside dotted with villages every few miles. It is closer to an ocean with a few drifting specks, and the ocean is so wide that even the horizon metaphor gives up and has a quiet lie down. Gravity, though, does not give up. Across this enormous stretch, the Milky Way and Andromeda pull on each other. That mutual pull is part of why Andromeda is moving toward us rather than simply receding with the general expansion of the universe. On the larger scales, space itself is expanding, and distant galaxies tend to move away from one another. But inside gravitationally bound groups, local attraction can overcome that expansion. The local group is one of these bound systems. The Milky Way, Andromeda, Triangulum, and many smaller galaxies are not simply being carried apart like crumbs on rising dough. They are connected by gravity strongly enough to form a shared neighbourhood. Still, the future path of the Milky Way and Andromeda is not as simple as older descriptions sometimes made it sound. The general expectation has long been that the two galaxies would eventually interact or merge billions of years from now. More recent studies have explored how uncertainties in mass, motion, and the influence of other galaxies, especially the Large Magellanic Cloud and Triangulum, may affect the outcome. This does not make the present distance any less astonishing. If anything, it makes the system more interesting. The empty ocean is not a straight road with a guaranteed destination sign at the end. It is a dynamic gravitational region where several large players shape the future, slowly and subtly. From Earth, all of this is hidden behind a simple view. Andromeda looks like a faint patch under dark skies. The Milky Way looks like a pale river overhead, if light pollution allows it. The space between them looks like night. But behind that quiet view is a structure of almost unbelievable depth. Our galaxy's halo extends outward. Andromeda's halo extends outward. Dwarf galaxies move through the local group. Gas drifts in thin envelopes. Dark matter shapes the motions of everything we can see. Light crosses the gulf with ancient news. Gravity connects the two great spirals across millions of years of travel time. So the empty ocean is empty only if we mean it is not filled with stars the way a galaxy is. It is empty only compared with the bright crowded disks where stars are born and orbit by the hundreds of billions. But in another sense, it is full of the things that make galaxies more than just collections of stars. It is full of halos, history, faint matter, motion and messages. It is the space where our local cosmic story stretches from one great spiral to another, and perhaps that is the right way to hold it in the mind tonight. Not as a blank distance to be crossed, and not as a terrifying void, but as a vast, thin, quiet region that teaches us how large nearby can be. The Milky Way and Andromeda are neighbours, but they are neighbours separated by a gulf so wide that light itself has to become ancient to cross it. Their visible disks are far apart, but their wider halos reach into the darkness between them. At first glance, telescope images can make the universe look strangely crowded. A deep photograph of space may show galaxies scattered everywhere. Tiny ovals, spirals, smudges, arcs, dots, and stretched little streaks of light. Some seem to sit almost on top of one another. Some look close enough to touch. A bright spiral may appear beside a red elliptical galaxy, while another faint little shape hovers just above it, as if the whole universe has been sprinkled across the sky like crumbs on a dark tablecloth. And it is easy, very easy to look at such an image and think, well, perhaps galaxies are not so far apart after all. Perhaps they are gathered together more tightly than we imagined. Perhaps space, at the larger scales, is more like a crowded room than an empty ocean. Then the measurements arrive, gently but firmly, and spoil that comforting illusion. The problem is not that the images are wrong. The images are doing exactly what they are supposed to do. They collect light from objects across the universe and place that light on a flat surface for our eyes to understand. The problem is that our eyes and brains are not naturally built to interpret cosmic depth. We are very good at judging ordinary distance. We can tell whether a cup is within reach, whether a car is too close, whether a chair is waiting in the darkness to attack our shin. These are useful survival skills. But when we look at a telescope image, we are not seeing space the way we see a room, we are seeing a projection. A three-dimensional universe has been pressed into a two-dimensional picture. Depth has been folded flat. That means two galaxies that appear close together in an image may not be close in space at all. They may only be close in our line of sight. One could be relatively nearby, and another could be billions of light years behind it. From Earth, they appear side by side because their light reaches us from nearly the same direction. It is a little like looking out of a window and seeing a bird on a tree branch with the moon behind it. For one brief view, the bird and the moon may appear near each other. You might even take a photograph where the bird seems to perch beside the moon, which would be a very impressive bird if true. But the bird is only a few meters or maybe a few dozen meters away, while the moon is hundreds of thousands of kilometers away. The closeness is visual, not physical. The same thing happens in images of galaxies, but on far larger scales. The sky is not a wall with objects pinned to it. It is more like a long tunnel of sight extending outward from Earth. Everything along that tunnel can appear in the same patch of sky. Nearby stars in our own galaxy may be in the foreground. Behind them may lie a galaxy millions of light years away. Behind that may be another galaxy hundreds of millions of light years away. Farther still, there may be galaxies whose light has been travelling for most of cosmic history. All of them can be captured in one image, stacked along the same viewing direction, like layers of glass with pictures painted on them. From our angle, the layers overlap. In reality, they're separated by depth so large that the word depth starts to feel underqualified. This is why deep field images are so powerful and so misleading at the same time. They reveal a sky full of galaxies, which is true. They show that even a tiny patch of apparently empty sky can contain thousands of galaxies, which is astonishing. But they also flatten the universe into a single frame, which can make the galaxies seem crowded in a way they are not. The image is crowded with light. space itself is still mostly distance. Think of standing in a long city street at night. From your position, the lamps may appear close together, especially if they line up along the road. A lamp 2 meters away, another 20 meters away, another 200 meters away, and another far in the distance can all seem to stack into one narrow line. A photograph might make them look almost touching. But if you walked the street, you would feel the gaps. You would pass through stretches of pavement, air, doorways, parked cars, and quiet spaces between each pool of light. The photograph compresses the distance. The walk reveals it. Astronomy often gives us the photograph, not the walk. And this is where galaxy images can quietly trick the imagination. When we see a cluster of galaxies in a telescope image, we may think of them as sitting together like marbles in a bowl. Sometimes they really are part of a galaxy cluster, bound by gravity, interacting, orbiting, merging and reshaping one another over time. But even then, the distances between individual galaxies are enormous. A galaxy cluster is crowded only by cosmic standards. By human standards, it is still mostly empty space. The galaxies inside it may be millions of light years apart, even while belonging to the same gravitational family. It is like saying people are packed closely together because they all live on the same continent. True, from far enough away. Not very helpful when you're trying to borrow a cup of sugar. Our own local group is a good example. The Milky Way, Andromeda, Triangulum, and many smaller galaxies are all part of the same gravitational neighbourhood. On a cosmic map, they form a small group. But Andromeda is still about 2.5 million light-years away from us. Triangulum is even farther, roughly in the same general region near Andromeda. The Large Magellanic Cloud is much closer, but still about 160,000 light-years away. These are our neighbours, these are the nearby houses in the galactic village, and yet the distances between them are so large that light needs hundreds of thousands or millions of years to cross them. This gap between appearance and reality is partly caused by scale. Galaxies themselves are huge, but the distances between galaxies are usually much larger than the galaxy's visible sizes. The Milky Way is around 100,000 light-years across, maybe more depending on how we define its outer parts. Andromeda's visible disk is also enormous, but the space between the two galaxies is measured in millions of light-years. If you made a simple scale model where the Milky Way were a dinner plate, Andromeda would not be another plate touching its edge. It would be another plate many plate widths away, and those plates would still be sitting inside even larger halos of dark matter and gas, so the model would become messy very quickly, as most honest models of the universe eventually do. The photographs do not show that separation easily. A telescope image captures angular size, not physical size directly. Angular size is how large something appears in the sky. The moon appears about 1/2 degree across. Your thumb held at arm's length covers a patch of sky much larger than many galaxies, even though your thumb is, hopefully, not larger than a galaxy. Apparent size depends on both real size and distance. A small object nearby can look large. A huge object far away can look small. A galaxy containing hundreds of billions of stars can become a faint little oval on an image, because it's so far away that its light is spread and dimmed across deep space. Andromeda shows this beautifully. It is actually much larger in the sky than many people expect. Under dark skies, its faint outer parts cover an area several times wider than the full moon. But because it is dim and diffuse, our eyes usually detect only the bright central region, a small misty patch. Photographs reveal more of it with long exposures. Still, even that large apparent size does not mean it is close in any everyday sense. It is physically huge and far away at the same time. The mind does not like holding both facts together, but the universe does not seem overly concerned with our preferences. For more distant galaxies, the situation becomes even more challenging. A galaxy billions of light-years away may appear as a tiny dot or smudge, barely different from a star at first glance. But unlike a star, that dot may represent an entire system of billions of stars. Its light has crossed a large fraction of the observable universe to reach us. It may be redshifted by the expansion of space. It may be dimmed by distance and altered by dust. It may appear close in the image to another galaxy that is actually nowhere near it. Without measuring distance, we cannot assume that neighbours on the screen are neighbours in space. This is why astronomers care so much about distance indicators. A sky position is only part of the story. To understand where a galaxy truly is, scientists need to know how far away it lies along our line of sight. That can involve measuring redshift, using standard candles, studying certain types of variable stars, observing supernovae, or applying other methods depending on the distance involved. Each method has its own range and uncertainty. Astronomy is, in many ways, the art of turning light into location. A galaxy's glow tells us not only that it exists, but how fast it may be moving away, how old its light is, what it contains, and where it belongs in the cosmic web. Until that distance is measured, an image can be visually beautiful but spatially ambiguous. It shows us direction, brightness, shape, and colour. It does not automatically show us depth. Imagine being handed a photograph of people standing in a field, but the photograph has been taken with a long lens that compresses distance. A person in the foreground and another far behind may appear almost side by side. Without other clues, you might misread the scene. Telescopes can create a similar effect at cosmic scale. The universe is not lying, it is simply being viewed from one position. There is another reason galaxies can look close: real gravitational lensing. Massive objects such as galaxy clusters can bend the path of light from more distant galaxies behind them. This happens because mass curves space-time, and light follows those curved paths. The result can be beautiful and strange. A distant galaxy may appear stretched into an arc. Sometimes one galaxy can appear as multiple images, mirrored or repeated around the foreground mass. In such cases, the image becomes even less straightforward. A curved orange streak beside a cluster may not be a nearby object in the cluster at all. It may be a far more distant galaxy, whose light has been bent around the cluster on its way to us. The sky becomes a natural telescope, but also a hall of mirrors. That phrase, hall of mirrors, is useful as long as we keep it grounded. Gravitational lensing does not create false galaxies. It redirects real light from real objects. But it can change where those objects appear, stretch their shapes, magnify them, or show them more than once. A galaxy may look close to a cluster because the cluster's gravity has bent its light into view. In reality, it may lie far behind the cluster. Without careful analysis, visual closeness can be deeply misleading. This can be especially surprising in famous space images, where foreground stars from the Milky Way, middle-distance galaxies, and distant background galaxies all share the same frame. A bright star with diffraction spikes may sit in front of countless remote galaxies. The star belongs to our own galaxy, and may be thousands of light-years away. The galaxies behind it may be millions or billions of light-years away. In the picture they coexist peacefully like objects on a page. In space they are separated by distances so large that calling them separated feels too mild. So why does this matter? It matters because images shape our instincts. If galaxies look close, we may subconsciously imagine that travel between them is just a harder version of travel between planets. First the Moon, then Mars, then another star, then another galaxy. A neat ladder of ambition. But the ladder has missing rungs wider than civilizations. The jump from planet to star is enormous. The jump from star to galaxy-wide travel is larger still. The jump from one galaxy to another is not just a longer trip. It is a different category of distance. Consider the difference between crossing the solar system and crossing to Andromeda. Light from the Sun reaches Earth in about 8 minutes. Light can cross the orbit of Neptune in a matter of hours, That is already vast, yet light takes about 2.5 million years to reach us from Andromeda. If the solar system is a room, the nearest major galaxy is not the next room, it is not even the next building. It is so far away that all ordinary architecture fails. The comparison becomes less like walking through a house and more like trying to cross a map where each centimetre represents an era. This is why almost unreachable is not just dramatic wording. With current physics and technology, travelling to another galaxy is beyond us in any practical sense. Even reaching nearby stars would be a multi-generational challenge unless we develop radically faster propulsion. Reaching a satellite galaxy like the Large Magellanic Cloud would require crossing distances tens of thousands of times greater than the nearest star. Reaching Andromeda would be farther again by another huge factor. At the speeds of our present spacecraft, the time required would be so long that the spacecraft itself would need to survive spans that dwarf recorded history. It would have to endure radiation, impacts from tiny particles, mechanical decay, power problems, navigation challenges, and the simple fact that the universe does not provide service stations between galaxies. Even if we imagined a future spacecraft travelling at a significant fraction of the speed of light, Andromeda would remain a journey of millions of years from Earth's point of view if the speed were not extremely close to light speed. Relativity adds complications for travellers moving very fast, but it does not make the distance disappear. The gap is real. It is not a misunderstanding caused by poor planning. The space between galaxies is one of the strongest reminders that the universe was not built around human convenience. And yet, there is a gentle upside. We cannot travel easily between galaxies, but we can see them. That is one of the great strange privileges of being alive in a transparent universe. Light crosses distances that bodies cannot. A galaxy can be unreachable and visible at the same time. In fact, most of astronomy exists in that gap. We study things we will never touch. We learn from light we did not send for. We build knowledge from messages that began travelling before humans existed, before mammals existed, sometimes before Earth had complex life. The unreachable does not become unknowable. It becomes something we approach with instruments, patience, mathematics, and imagination that has been carefully trained not to run too far ahead of the facts. This also explains why telescope images can feel intimate even when the objects are remote. A photograph brings a galaxy into the palm of your hand, onto a screen, into a quiet room. You can zoom in. You can notice spiral arms, dust lanes, bright cores, star-forming regions, or distorted shapes. The image creates nearness of attention, not nearness of location. You're not close to the galaxy. Your mind is close to the evidence. That distinction is important and rather lovely. Science does not shrink the universe physically. It gives us better ways to relate to its size. There is also a selection effect at work in what we notice. We tend to see the bright parts of galaxies. We notice cores, arms, star-forming regions, and glowing structures. We do not easily notice the darkness around and between them. In a photograph, the black background can feel like empty backdrop, as if it is simply the canvas on which the important objects are painted. But that blackness is not just background. It represents real distance. In many images, the dark space between two visible galaxies may correspond to millions of light years. The quiet part of the image may be the largest part of the story. If you look at a galaxy pair that is truly interacting, the closeness is more real. Some galaxies are close enough for gravity to distort them. They may pull out tidal tails, streams of stars, and bridges of gas. They may trigger bursts of star formation. Their shapes may bend or stretch under mutual influence. These systems are not just aligned by chance, they are physically near enough to affect one another. But even here, near remains cosmic. The galaxies may be separated by tens or hundreds of thousands of light years. Their outer halos may overlap long before their bright centers come close. The interaction unfolds over hundreds of millions of years. A photograph may catch a dramatic stage, but the drama is slow. If you could watch with ordinary human eyes over a lifetime, almost nothing would visibly move. The universe does not rush its special effects. This slowness is part of why galaxies can appear static and decorative in images. They look like objects placed in position. But galaxies are moving. They rotate. They orbit within groups and clusters. They fall toward one another. They merge. They grow. They are shaped by dark matter and gas. The problem is that their timescales are enormous. A galaxy rotation may take hundreds of millions of years. A merger may take billions. The picture is not still because nothing is happening. It is still because we are brief. We are looking at a single frame from a film so long that our whole species has watched only a blink of it. That briefness affects how we imagine distance too. In human life, a place that cannot be reached within a lifetime feels almost unreal. But galaxies remain real whether or not we can visit them. The universe is not divided into places for humans and places that do not count. The unreachable galaxies are still full of stars, planets, gas, dust, black holes, and histories. Some may contain worlds with skies and landscapes of their own. Some may be old and quiet. Some may be young and turbulent. Some may already have changed since the light we see left them. Our inability to travel there does not reduce them. It only reminds us of the limits of our bodies and machines. The strange thing is that images both hide and reveal this truth. They hide distance by flattening depth. They reveal abundance by showing how many galaxies exist. They make the cosmos feel close enough to admire, while the measurements remind us that admiration is not arrival. A galaxy can sit on your screen beside another galaxy, separated by a finger's width, while in reality the distance between them might be so large that light has been crossing it for millions or billions of years. The screen makes neighbours of everything. Space does not. So when galaxies look close, the first question is always, close in the sky or close in space? Those are very different things. Close in the sky means they appear near the same direction from Earth. Close in space means they are physically near each other in 3 dimensions. Astronomers need distance measurements to tell the difference. Without them, a crowded image is like a crowd seen from far away through fog. Some people may be shoulder to shoulder. Others may be standing on a hill much farther back. Only careful measurement reveals the arrangement. This is the heart of the illusion. The universe gives us a sky, and the sky gives us directions. But distance has to be earned. It has to be measured, inferred, cross-checked, and placed into a 3-dimensional map. Once that happens, the crowded picture opens up. The galaxies pull apart, foreground and background separate. A flat field becomes a deep volume. What looked like a handful of glitter becomes an enormous arrangement of objects spread through cosmic time. And once we understand that, the unreachable distance becomes easier to respect. The galaxies in a deep field image are not beads lying on black velvet. They are whole systems distributed through space and time, some nearer, some unimaginably farther. Their light arriving together only because our telescope gathered it in one direction. We see them side by side, not because they are side by side, but because the universe is deep and we are looking through it. That idea changes the way a galaxy image feels. The next time you see one, you might pause before thinking of the blackness as empty, or the galaxies as close. You might imagine the image unfolding away from you, layer after layer, with some galaxies in the foreground, others far behind, and others so distant that their light began travelling when the universe itself was young. The picture becomes less like a painting, and more like a narrow window through a vast building, with rooms behind rooms behind rooms, most of them too far away to enter, but not too far away to leave a trace of light. By this point, the darkness between galaxies has started to feel less like an empty background, and more like a real part of the universe, wide, quiet, and difficult to measure with anything our everyday minds understand. And that brings us to a very practical question. If galaxies are so far away that we cannot travel to them, and if telescope images flatten the universe into a beautiful but misleading picture, how do we know how far away anything really is? How do we turn a faint smudge of light into a distance? How does a tiny glow on a detector become a number like 2.5 million light years, or 50 million, or 10 billion? The answer, as it often is in astronomy, begins with light. Not because light makes everything easy, because it certainly does not. Light can be dimmed, stretched, scattered, absorbed, blended with other light, and generally behave like a very informative but slightly cryptic messenger. But light is what reaches us. We cannot send a measuring tape to Andromeda. We cannot lean across the local group with a ruler, squint at the markings and say, yes, that is definitely farther than the shed. We have light, and from that light, astronomers have learned to build distance. This is one of the most remarkable things humans have ever done. From a small planet orbiting one star inside one galaxy, we have measured the scale of galaxies far beyond our own. We have done it without touching them. We have done it without visiting them. We have done it by noticing patterns, comparing brightness, studying colour, watching stars pulse, and reading the stretching of light itself. It is like trying to map a continent by studying postcards thrown into the sea, except the postcards are made of photons, the sea is space-time, and some of the postcards were mailed before Earth had grass. The first step is to understand that brightness is not as simple as it looks. Something can appear faint because it is small, because it is genuinely dim, because it is hidden behind dust, or because it is very far away. A candle nearby can outshine a lighthouse far away if you're standing close enough to the candle. A bright object at a great distance may look faint, while a dim object nearby may look similar. Apparent brightness alone does not tell us distance. It gives us a clue, but not the full answer. To know how far away something is, we need to know how bright it really is, not just how bright it looks from here. This difference between apparent brightness and true brightness is one of the basic tools of cosmic measurement. If you know how luminous an object actually is, and you measure how bright it appears, then you can estimate its distance. The farther away it is, the more its light spreads out before reaching you, and the fainter it appears. This is familiar in ordinary life. A street lamp looks bright when you stand beneath it and dimmer when you walk away. The lamp has not changed. You have, or perhaps you have simply remembered that you left something at home and are now walking back, which is not quite astronomy, but the principle is sound. The difficulty is finding objects whose true brightness we know. Astronomers call these standard candles, though they are not candles in any normal sense. Please do not try to put one on a birthday cake. A standard candle is an object or event with a known or predictable luminosity. If we can identify such an object in a galaxy, we can compare its true brightness with how bright it appears and work out how far away it must be. The challenge is that different standard candles work at different distances. Some are useful nearby, others can be seen across much larger stretches of the universe. So astronomers build what is called the cosmic distance ladder. The word ladder is helpful because each method rests on the one below it. You cannot leap straight to the farthest galaxies without first calibrating the nearer steps. You start close, where measurements are most direct. Then you use those nearby measurements to understand objects a little farther away. Those objects then help calibrate brighter markers that can be seen farther still. It is a careful chain of trust, rung by rung, from the local neighbourhood to the distant universe. A bit like measuring a very long hallway by first proving your ruler is the right length, then using it to mark a rope, then using the rope to measure the next section, and so on, while the hallway is dark, ancient, expanding, and full of stars. The lowest rungs begin with geometry. For nearby stars, astronomers can use parallax. This is the tiny apparent shift in a star's position when viewed from different points in Earth's orbit around the Sun. Hold a finger in front of your face and look at it with one eye, then the other. Your finger seems to jump against the background. It has not moved. Your viewpoint has changed. Stars do the same thing, but the shift is extremely small because they are so far away. By measuring that tiny shift, astronomers can calculate distance directly. Parallax is one of the cleanest methods we have because it is based on geometry rather than assumptions about brightness. But parallax only works out to a limited range, even with very good instruments. Beyond that, the apparent shift becomes too small to measure accurately. So astronomers use nearby distances from parallax to calibrate other objects, including a special kind of star called a Cepheid variable. Cepheids are stars that brighten and dim in a regular rhythm. They pulse. Their outer layers expand and contract, causing their brightness to rise and fall over a period of days or weeks. The wonderful thing about Cepheids is that the length of the pulse is related to the star's true brightness. A Cepheid that pulses slowly is intrinsically brighter than one that pulses quickly. So by watching how long a Cepheid takes to brighten and fade, astronomers can work out how luminous it really is. Once you know that, you can compare true brightness with apparent brightness and estimate distance. Cepheids became one of the great keys to the scale of the universe. They helped prove that some of the fuzzy spiral nebulae seen through telescopes were not small clouds inside the Milky Way, but entire galaxies far beyond it. Before that realization, many people thought the Milky Way might be the whole universe. A cozy thought, perhaps, but a little like thinking your bedroom is the entire house because you have not opened the door yet. Cepheids helped open the door. One of the most famous uses of Cepheids came when astronomers measured distances to stars in the Andromeda galaxy. Once those distances were calculated, it became clear that Andromeda was far outside the Milky Way. It was not a nearby cloud. It was another galaxy. This changed the human picture of the universe almost completely. The Milky Way went from being the universe itself to being one galaxy among many. Imagine discovering that your town, which you thought was the whole world, is actually one small settlement on a planet full of continents. Then imagine discovering that the planet is one of many, the star is one of many, the galaxy is one of many, and the universe has been politely not mentioning this while you were busy looking for your socks. Cepheids are powerful, but they cannot take us all the way across the observable universe. They are stars, and stars grow too faint to measure individually at very large distances. For farther galaxies, astronomers need brighter markers. One of the most important is the Type 1a supernova. This is a particular kind of stellar explosion, involving a white dwarf in a system where conditions lead to a sudden thermonuclear runaway. The details are complex, but the important point for distance measurement is that Type 1a supernovae have predictable brightness patterns. They are not all perfectly identical, but their light curves can be standardized. That means astronomers can use them as extremely bright distance indicators. A Type 1. A supernova can briefly shine with the brightness of billions of stars. That makes it visible across enormous distances, far beyond where individual Cepheid variables can be studied easily, but again, the latter matters. To use Type 1a supernovae confidently, astronomers first need to calibrate them in galaxies where distances are known by other methods, such as Cepheids. Once the true brightness of these supernovae is well understood, they can be used to measure distances to much farther galaxies. It is a relay race made of light. Cepheids pass the baton to supernovae. Supernovae carry it deeper into the universe. This is where the distance ladder becomes both elegant and fragile. Each rung depends on careful calibration. Dust can make objects look dimmer and redder than they really are. Metal content, meaning the abundance of elements heavier than hydrogen and helium, can influence stellar properties. Observations have uncertainties. Instruments need calibration. Galaxies are not always tidy laboratories. A star may sit in a crowded field. A supernova may occur in a galaxy with dust along the line of sight. The universe is generous with information, but it does not label everything clearly. There are no little tags saying, "This light has been dimmed by dust by exactly this amount. Thank you for your patience." So astronomers compare, correct, repeat, and cross-check. They use different wavelengths of light. Infrared can pass through dust better than visible light. They observe multiple objects. They compare independent methods. They use space telescopes to avoid the blurring effects of Earth's atmosphere. They look for consistency. Distance measurement is not a single dramatic moment where someone points at a galaxy and announces a number. It is a careful process, built from many observations with uncertainties attached. That may sound less exciting, but it is actually more impressive. The universe is not being guessed. It is being measured with humility. For even more distant galaxies, another clue becomes essential: redshift. When light from a galaxy is stretched toward longer, redder wavelengths, astronomers can measure that shift. In many cases, especially on large cosmic scales, this redshift is tied to the expansion of space. The universe is expanding, which means that as light travels through space over millions or billions of years, the stretching of space stretches the light as well. The farther away many galaxies are, the more their light has been redshifted. This relationship was one of the great discoveries of modern cosmology. It showed that galaxies are not simply sitting in a static universe. On large scales, they are moving away from one another because space itself is expanding. This does not mean galaxies are flying away through space like sparks from a firework in the simple everyday sense. A better way to think about it is that the space between distant galaxies is growing. The classic example is dots on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because each dot is crawling across the balloon, but because the surface itself stretches. Like most analogies, this one eventually becomes a little wobbly if you push it too hard, and it should not be taken as a literal picture of the universe expanding into something else. But it helps with the basic idea. The distance between faraway galaxies can increase because space itself changes. Redshift gives astronomers a way to estimate distance, especially for faraway galaxies where other methods are difficult. But it is not quite as simple as saying redder equals farther in every situation. Nearby galaxies can have local motions due to gravity. Andromeda, for example, is moving toward us, so its light is blue-shifted rather than red-shifted. Galaxies inside clusters can move around in complicated ways. On smaller scales, gravity can override the general expansion, but for very distant galaxies, redshift becomes a powerful guide. It tells us how much the universe has expanded since the light began its journey. It also tells us that when we look far away, we look back into a younger universe. That last idea is worth resting with for a moment. Measuring distance with light also measures time. A galaxy 1 billion light-years away is seen as it was 1 billion years ago, because its light has taken that long to reach us. A galaxy 10 billion light-years away is seen as it was when the universe was much younger. The distance is not just a separation in space, it is a separation in history. The farther out we look, the deeper into the past we see. This is not a metaphor. It is the result of light having a finite speed. The universe comes to us delayed, layer by layer. So when astronomers measure distant galaxies, they are not only building a map, they are building a timeline. Nearby galaxies show us the more recent universe. Farther galaxies show us earlier stages. Very distant galaxies reveal a universe where galaxies were younger, smaller, more irregular, more active, or still assembling. By comparing galaxies at different distances, astronomers can study how galaxies change over time. Light turns distance into history. The sky becomes less like a ceiling and more like an archive. There is something deeply strange about that. If you look across a room, you see the other wall almost as it is now, because the light takes only a tiny fraction of a second to reach you. If you look at the moon, you see it as it was a little more than 1 second ago. The sun is about 8 minutes in the past. Nearby stars are years in the past, and galaxies may be millions or billions of years in the past. The same act of seeing operates on all these scales, but the time delay grows until it becomes almost impossible to ignore. Vision at cosmic distance is memory. The light itself carries more than brightness and redshift. It carries spectra, the spread of colours that reveals what matter is doing. When astronomers split light into a spectrum, they can see absorption and emission lines, fingerprints of atoms and molecules. Hydrogen leaves certain marks. Oxygen leaves others. Calcium, sodium, iron, and many more can be identified. These lines can reveal a galaxy's chemical composition, star formation, motion, temperature, and redshift. A faint beam of light can tell us what a galaxy contains, how its gas is moving, and how much its light has been stretched during the journey. That is a lot of gossip from a photon, and frankly, we appreciate its service. Spectroscopy is one of the great tools for making the universe three-dimensional. A telescope image can show where a galaxy appears on the sky. A spectrum can help reveal how far away it is and how it is moving. With enough galaxy positions and redshifts, astronomers can map large-scale structure. They can see galaxy clusters, filaments, sheets, and voids. The universe is not arranged randomly like dust shaken onto black paper. It has a cosmic web structure, shaped by gravity and dark matter over billions of years. Galaxies gather along filaments. Clusters form where filaments meet. Vast voids open between them. Light measurement gives us access to that structure. And yet every measurement begins with something arriving here. A photon enters a telescope. A detector records it. Software processes it. Scientists compare it with models, calibrations, and other data. The distance to a galaxy may sound like a single number, but behind it is a chain of work. Someone measured a star's parallax. Someone observed Cepheids. Someone calibrated supernovae. Someone measured redshifts. Someone corrected for dust. Someone checked the uncertainty. The final number is not just a fact floating alone. It is a carefully built bridge from the nearby to the faraway. This is why uncertainty is not a weakness in science. It is part of honesty. When astronomers say a galaxy is a certain distance away, there is often an uncertainty range. The farther and fainter the object, the more careful we have to be. Different methods may give slightly different results. Some debates remain active, such as the exact rate of cosmic expansion. This does not mean the whole structure collapses. It means the measurements are precise enough that disagreements become meaningful. The universe is not vague. Our tools are becoming sharp enough to notice where the remaining puzzles are. For the purpose of imagining galaxy distances, the key point is simple. We know these distances because light allows us to compare, calibrate, and infer. Nearby geometry anchors the ladder. Pulsating stars extend it. Supernovae carry it farther. Redshift opens the wider universe. Spectra reveal motion and composition. Together, these methods transform faint objects into places with distances, ages, and relationships. A galaxy is no longer just a smudge. It becomes part of a map. But there is a quiet emotional twist in all this. The light we use to measure galaxies left those galaxies long before it reached us. We are always working with delayed information, and yet that delay is exactly what makes cosmic history visible. If light travelled instantly, the universe might be easier to navigate perhaps, but harder to understand in time. Because light takes time, the distant universe preserves earlier eras. The very inconvenience that makes galaxies unreachable also makes them readable. The unreachable becomes measurable. That may be one of the most beautiful practical truths in astronomy. We cannot visit Andromeda, but we can measure its distance. We cannot fly to a galaxy cluster billions of light years away, but we can study its redshift, its galaxies, its mass, and sometimes even the way it bends light behind it. We cannot step into the early universe, but we can receive ancient light and learn from it. Distance limits our bodies. It does not entirely limit our understanding. So when a galaxy looks close in an image, light gives us the tools to ask where it truly sits. Is it a nearby dwarf galaxy? A faraway spiral? A background galaxy magnified by gravity? A member of a cluster? A young galaxy whose light has crossed most of cosmic time? The image invites the question. Measurement begins the answer, and with each answer, the flat sky deepens. The galaxies separate into layers. The universe becomes less like a picture and more like a vast arrangement of distances, motions, and histories. This is why measuring the universe with light feels almost like learning to listen properly. At first, the sky is a quiet darkness with points and smudges. Then the light is separated, compared, timed, and understood. The smudge becomes a galaxy. The colour becomes a redshift. The pulse becomes a distance. The explosion becomes a rung on a ladder. The faint line in a spectrum becomes a clue to motion across billions of years. Nothing in the night sky is as simple as it first appears, which is inconvenient for quick explanations, but very good for wonder. Once light has given the universe some depth again, the galaxies stop looking like scattered marks on a flat sky and begin to arrange themselves into neighbourhoods. Not neighbourhoods in the ordinary sense, of course. There are no streets, no fences, no little corner shops, no one leaning over to ask whether you remembered to put the bins out. A galactic neighbourhood is built from gravity, distance, motion, and time. Its members may be separated by hundreds of thousands or millions of light years, and yet they still belong together more than they belong to the wider expansion beyond them. They share a region of space. They tug on one another. They carry records of old encounters and future possibilities, and our own galaxy, the Milky Way, lives inside one of these small cosmic gatherings. This gathering is called the local group, which sounds almost comically modest for something spread across millions of light years. The name has the same energy as calling the Atlantic Ocean the nearby puddle, but in astronomy, local is a flexible word. It does not mean close enough to visit. It does not mean close enough to send a message and expect a reply before everyone forgets what the question was. It means close compared with the truly vast structure of the universe. The local group is our immediate galactic environment, the collection of galaxies around the Milky Way that are close enough and gravitationally connected enough to form a shared system. At the heart of this neighbourhood are two large galaxies, the Milky Way and Andromeda. These are the big residents, the major spirals, the two broad star cities around which many smaller galaxies move. The Milky Way is our home, a disk of hundreds of billions of stars with a central bulge, spiral arms, dust lanes, gas clouds, a dark matter halo, and one small planet where a species has learned to worry about emails and measure galaxies with light. Andromeda, also known as M31, is the other giant, a large spiral galaxy roughly 2.5 million light-years away. If the local group had a quiet council meeting, these two would take up most of the gravitational seating. Then there is Triangulum, or M33, another spiral galaxy, smaller than the Milky Way and Andromeda, but still a major member of the group. Triangulum is sometimes easy to overlook in popular descriptions, because Andromeda tends to receive the dramatic attention, perhaps because it is larger, brighter, and often mentioned in future merger stories. But Triangulum matters. It has spiral arms, star-forming regions, and its own place in the dynamics of the local group. It may be gravitationally connected to Andromeda in complicated ways. It is not just a background guest, it is part of the neighbourhood structure. Around these larger galaxies are many smaller ones, dwarf galaxies that can be faint, fragile, and difficult to find. Some orbit the Milky Way, some orbit Andromeda. Some move more independently through the local group. These dwarfs range from systems with billions of stars to very faint collections containing far fewer. A dwarf galaxy may sound small, and compared with the Milky Way it is, but we should be careful. Small by galactic standards can still mean a system large enough to contain more stars than the human mind can comfortably count before bedtime. Astronomy has a habit of using modest words for enormous things. Dwarf galaxy, local group, nearby universe, all very calm phrases for distances that would make a travel agent quietly resign. The Large and Small Magellanic Clouds are two of the Milky Way's most famous satellite galaxies. They are visible from the southern sky and look like pale, detached clouds, which is how they earned their common name. The Large Magellanic Cloud is not just a faint smudge. It is a real galaxy with billions of stars, gas, dust, old star clusters, and active star-forming regions. The Small Magellanic Cloud is smaller and more irregular, stretched and influenced by its interactions with the Milky Way and the Large Magellanic Cloud. These galaxies are close companions in the local group, but again, close does not mean near in any human way. Their light still takes hundreds of thousands of years to reach us. Other dwarf galaxies are far harder to see. Some are dim because they contain relatively few stars. Others are spread out over large areas of sky, making them low in surface brightness. That means they do not stand out sharply against the background. Finding them can require careful surveys, sensitive instruments, and a lot of patient data analysis. It is not always a matter of simply pointing a telescope and seeing a tiny galaxy waving back. Some dwarf galaxies are more like whispers in the data, faint patterns of stars moving together or sitting at similar distances. They are real, but they are subtle. This matters because dwarf galaxies are not just minor decorations around the big spirals. They help astronomers understand how galaxies form and grow. In the current picture of cosmic history, large galaxies build themselves partly by merging with and absorbing smaller systems over billions of years. The Milky Way did not appear complete all at once, like a finished dinner placed on the table. It grew, gathered material, formed stars, and consumed smaller galaxies. Some of that process is still visible today in streams of stars looping through the Milky Way's halo, remnants of smaller galaxies pulled apart by gravity. These stellar streams are like trails left behind after long, slow meals, which is perhaps not the most elegant image, but gravity is not always tidy. The Sagittarius dwarf spheroidal galaxy is one example of a small galaxy being disrupted by the Milky Way. It has been stretched into streams as it orbits and passes through our galaxy's outer regions. Its stars are being pulled into the Milky Way's halo, gradually losing their old identity as a separate system. This is not violent in the way a crash is violent. It is slow, stretched across immense time, but it is still a kind of galactic transformation. The smaller system is being unmade and folded into the larger one. In the far future, some stars in the Milky Way's halo may have begun their lives in galaxies that no longer exist as separate objects. Andromeda has its own family of satellite galaxies too. Some are small elliptical companions visible in images near its bright disk, while others are faint dwarf spheroidals scattered through its halo and beyond. Andromeda's surroundings appear rich and complex. It has streams, satellite systems, and signs of past interactions. In many ways, Andromeda is not just one galaxy, but the centre of its own local sub-neighbourhood inside the local group. The Milky Way and Andromeda each have their own families, and the whole local group can be thought of as two main gatherings, with smaller galaxies spread around them, along with Triangulum and other members moving through the shared gravitational environment. This helps explain why the local group is not shaped like a neat ball of galaxies evenly sprinkled in every direction. It is structured. It has concentrations around the large galaxies. It has satellite systems. It has spaces between. It has motion shaped by gravity and by the history of how matter gathered after the Big Bang. A map of the local group would not look like a clean classroom diagram with evenly spaced dots. It would look more irregular, with large members, small companions, faint outskirts, and uncertain boundaries. The universe is not especially fond of straight lines and tidy labels, no matter how much we might appreciate them before sleep. One of the most important things about the local group is that it is gravitationally bound. On very large scales, the universe is expanding. Distant galaxies tend to move away from us because the space between galaxy groups and clusters is stretching. But inside bound systems, gravity can overcome that expansion. The Earth is not expanding away from the Sun. The stars inside the Milky Way are not being pulled apart by cosmic expansion, and the galaxies inside the local group are not simply drifting away from one another with the general flow. Their mutual gravity matters more at this scale. This is why Andromeda can be moving toward the Milky Way even though far more distant galaxies are generally receding. That can feel confusing at first. We hear that the universe is expanding, and then we hear that Andromeda is approaching us. Both are true. Expansion dominates on very large scales, especially between galaxy groups and clusters that are not gravitationally bound to each other. But local gravity can create local motion. If you imagine raisins in rising dough, the raisins move apart as the dough expands. But if two raisins were tied together by an invisible elastic thread, strong enough to resist the expansion, they could remain together or even move closer. The local group is more like that. Its galaxies are held in a shared gravitational relationship, while the larger universe expands beyond it. The future of the Milky Way and Andromeda has often been described as a coming merger, expected billions of years from now. That may still happen, but more recent studies have shown that predicting these long-term paths is not as simple as once thought. The exact motion of Andromeda, the mass of the Milky Way, the influence of Triangulum, and the growing importance of the Large Magellanic Cloud all affect the calculation. The future is not a single fixed scene we can casually circle on a calendar. It is a set of possibilities, shaped by measurements that are improving over time. This is a good reminder that science does not freeze the universe into certainty. It updates the picture as the evidence gets better. Even so, the relationship between the Milky Way and Andromeda remains central to the local group. They are the two dominant galaxies, and their gravity shapes much of the region. Whether they collide directly, pass at a distance first, or follow a more complicated sequence, they are not isolated strangers. They are part of the same small cosmic system. Their dark matter halos may reach far beyond their visible disks. Their satellite galaxies move under shared influences. The space between them is not empty background, but part of the environment that defines the local group. If the local group sounds large, it is. Several million light-years across, depending on how we define its edges, it is vastly bigger than anything a human can experience directly. But compared with galaxy clusters, superclusters, and the cosmic web, it is small. That is another scale trick. The local group is enormous compared with us, modest compared with the universe. It is like being told your house is tiny, only to discover the house is the size of a continent. Scale in astronomy is not a ladder with evenly spaced rungs. It is more like a staircase where each step suddenly becomes a mountain. Within this small cosmic neighborhood, the distances are already hard enough. The Large Magellanic Cloud is around 160,000 light-years away. Andromeda is about 2.5 million light-years away. Triangulum is millions of light-years away as well. Many dwarf galaxies are scattered across these ranges. Even moving at the speed of light, which no spacecraft with mass can do, crossing the local group would take millions of years. The whole thing is local only from the point of view of a universe that contains structures hundreds of millions or billions of light-years across. This is why the local group is a useful place to train the imagination. It gives us a middle scale. The solar system is too small, in cosmic terms, to prepare us for galaxies. The observable universe is too large to take in at once. The local group sits between those extremes. It is larger than a single galaxy, but still close enough for us to study its members in detail. We can observe individual stars in nearby dwarf galaxies. We can map stellar streams. We can study Andromeda's disk and halo. We can examine star formation in the Magellanic Clouds. We can watch how small galaxies interact with larger ones. The local group is distant, but it is not hopelessly remote. It is our laboratory for understanding galaxy behavior on a manageable cosmic scale. If manageable is allowed to mean millions of light-years, There is also something comforting in the idea that the Milky Way has neighbours. Not close neighbours, and certainly not chatty ones, but neighbours all the same. Our galaxy is not an isolated island drifting alone in an endless dark. It belongs to a family of galaxies, a loose and ancient gathering shaped by gravity. Some members are large and bright, some are faint and easily missed. Some are being pulled apart. Some may have already been absorbed. Some may still be waiting to be discovered in the dim outskirts of the group. The local group is not a static list. It is a living map, revised as astronomers find more faint galaxies and measure their motions more carefully. The faintest members are especially interesting because they connect galaxy astronomy with dark matter. Many dwarf galaxies contain relatively few stars but appear to have much more mass than their visible matter can explain. Their stars move as if there is additional unseen mass holding them together. This fits with the idea that dark matter plays a major role in galaxy formation. Dwarf galaxies may be small in starlight, but they can sit inside dark matter halos that shape their motion. Studying them helps astronomers test models of how structure formed in the early universe. So a tiny faint dwarf on the edge of detectability is not just a dim object, it is a clue to the invisible scaffolding of the cosmos. The local group also helps us understand what the Milky Way itself has been doing. We cannot see our galaxy from outside because we live inside it. That is a bit inconvenient, like trying to draw the shape of a forest while standing among the trees with fogged glasses. But by studying nearby galaxies, especially those similar to ours, we can infer what our own galaxy might look like from the outside. Andromeda gives us a large spiral for comparison. Triangulum offers a smaller spiral with active star formation. The Magellanic Clouds show irregular interacting satellite galaxies. Dwarf spheroidals show old, faint stellar systems. Together, the local group provides examples of many galaxy types close enough for detailed study. This is one of the reasons astronomers love nearby galaxies. They are not nearby in the travel sense, but they are nearby in the observing sense. Their stars can sometimes be resolved individually. Their histories can be reconstructed from stellar populations. Their gas can be mapped. Their motions can be measured. They let us study galaxies not only as smudges of combined light, but as systems built from stars and gas with individual histories. The local group is not only our neighbourhood, it is our reference collection. Think of it like studying weather. If you could only see Earth as a distant blue dot, you might know it had clouds. But if you were close enough to watch storms form, oceans circulate, seasons change, and clouds move over continents, you would understand much more. Nearby galaxies offer that kind of detail for galaxy evolution. Andromeda is not just a light in the sky. It is a galaxy whose stars, clusters, dust lanes, satellite systems, and halo can be studied. The Magellanic Clouds are not just patches. They are active laboratories where star formation, gas dynamics, and galaxy interaction can be examined at relatively close range. The local group lets astronomy zoom in. At the same time, it teaches humility, because even this zoomed-in neighbourhood is mostly space. The galaxies are separated by huge gaps. The smaller members are faint and scattered. The visible matter is only part of the mass. The bright disks are only part of the galaxies. The local group itself sits within a larger environment, influenced by nearby groups, clusters, voids, and the broader cosmic web. What feels like a neighbourhood from one scale becomes a dot from another. The local group is real and important, but it is also just one small gathering among countless others. If we could fly far outside it and look back, the local group might appear as a modest cluster of lights, with the Milky Way and Andromeda as the brightest spirals, Triangulum nearby, and many dwarfs barely visible or invisible without careful instruments. Beyond it would be other galaxy groups and clusters, spread along filaments and separated by larger voids. The local group would not look central. It would not glow with special importance. It would be one small arrangement in a vast cosmic network. And yet, for us, it is home territory. It is the first level above the Milky Way in our address. That cosmic address is worth saying slowly. Earth is in the solar system. The solar system is in the Milky Way. The Milky Way is in the local group. The local group is part of a larger region of nearby galaxies and flows, connected to the broader cosmic web. Each level changes the meaning of place. A street address tells someone where to bring a parcel. A cosmic address tells us how matter has gathered across billions of years. Both are useful, though one is much more likely to involve a delivery driver pretending they could not find the doorbell. The local group may be small compared with the universe, but it is large enough to contain many stories. It contains the long growth of the Milky Way. It contains Andromeda's massive spiral system and its surrounding satellites. It contains Triangulum, star-forming regions, dwarf galaxies, stellar streams, dark matter halos, gas clouds, and histories of past interactions. It contains future uncertainties, including how the largest members will move over billions of years. It contains galaxies that may be slowly dissolving, and galaxies that may remain separate for ages. It is not a quiet display case. It is a slow, gravitational conversation, and because this conversation unfolds over such long times, it is easy to mistake stillness for simplicity. From our brief human viewpoint, the local group seems frozen. Andromeda sits in the sky. The Magellanic Clouds glow in the south. Dwarf galaxies are catalogued in surveys. But over hundreds of millions and billions of years, the system changes. Satellites orbit and fall in. Gas is stripped. Stars are redistributed. Galaxies approach, miss, merge, or reshape. Gravity keeps writing the story in motions too slow for a lifetime to notice. That is why the local group is both cozy and immense. It is cozy because it is ours, the small collection of galaxies nearest to the Milky Way, the familiar local arrangement in the cosmic map. It is immense because every distance inside it is still almost beyond imagination. Our neighbourhood is millions of light years wide. Our nearest large neighbour is seen by ancient light. Our satellite galaxies are close enough to study, but far enough to remind us that closeness in astronomy is a very patient word. So as we picture the local group tonight, it may help to let go of the idea of a crowded cluster. Imagine instead a huge dark volume of space, with a few major galaxies and many smaller ones spread through it, all connected by gravity, all moving slowly, all carrying the marks of older encounters. The Milky Way is not alone in that volume. Andromeda shines across the gulf. Triangulum turns quietly nearby. Dwarf galaxies drift, orbit, stretch, fade, or wait to be found. Around the bright galaxies, unseen halos extend outward. Between them, light travels for ages, and gravity works without hurry. Beyond our local family of galaxies, the universe begins to reveal a pattern that is much larger and stranger than a simple scattering of islands. If we could somehow rise far above the Milky Way, above Andromeda, above the local group, and keep rising until whole collections of galaxies became small markings in the dark, we would not see galaxies spread evenly in every direction, like sugar dusted across a table. We would see structure. We would see galaxies gathered along long threads, broad sheets and dense knots, with enormous dark regions opening between them. The universe, on its largest visible scales, looks less like a smooth mist and more like a vast web. Galaxies collect along filaments. Clusters form where those filaments meet, and between those structures lie the great voids, immense regions where almost nothing lives. Almost nothing is the important phrase. A cosmic void is not a perfect empty box. It is not absolute nothingness. It is not a clean hole punched out of the universe, with a neat edge and a sign saying, "No galaxies beyond this point." Voids still contain matter. They may contain faint gas, dark matter, radiation, and some galaxies, usually much fewer than average. But compared with the bright crowded filaments and clusters, they are underdense. They are regions where the universe has very little in the way of galaxies. If a galaxy cluster is a busy city centre at lunchtime, A cosmic void is a huge empty countryside at 3 in the morning, except the countryside is tens or hundreds of millions of light years wide, and the nearest shop closed before the dinosaurs. This idea can feel surprising because we often imagine space as already empty. After all, even inside the Milky Way, stars are separated by huge distances. Between galaxies, the darkness grows wider still. So when astronomers say there are regions where space is emptier than usual, it sounds almost excessive. How empty can empty get? But the universe has levels of emptiness. Inside a galaxy, stars are sparse by human standards but common by cosmic standards. In a galaxy group, galaxies are separated by millions of light years, but they still form a recognizable neighborhood. In galaxy clusters, many galaxies gather under shared gravity. Along filaments, galaxies are strung out across huge distances, like beads on invisible threads. Then there are voids, where even galaxies become rare. To picture this, imagine a sponge. Not a neat kitchen sponge with one unfortunate smell you cannot quite identify, but a large three-dimensional sponge with walls, gaps, tunnels and holes. The material of the sponge represents the filaments and sheets, where galaxies are more common. The holes represent the voids. The important thing is that the holes are not separate from the sponge. They are part of the structure. The walls define the holes, and the holes define the walls. In the same way, cosmic voids are not mistakes in the universe. They are part of the large-scale pattern of matter. The universe is shaped not only by where galaxies gather, but also by where they do not. The reason this pattern exists goes back to the early universe. In its earlier stages, matter was spread very evenly, but not perfectly evenly. There were tiny variations in density, small places where matter was just a little more concentrated, and places where it was just a little less concentrated. Over billions of years, gravity amplified those tiny differences. Regions with slightly more matter pulled in more matter. They became denser. They formed galaxies, groups, clusters, and filaments. Regions with slightly less matter lost the competition. Matter flowed away from them toward denser areas. Over time, those under dense regions became voids, not because someone scooped them out, but because gravity slowly moved matter into the surrounding web. That slow movement gives voids a history. They are not passive empty rooms. They grow as matter drains away from them into filaments and clusters. Their edges can become more sharply defined over time as galaxies collect along boundaries. Smaller voids can merge into larger ones. The cosmic web evolves, and voids are part of that evolution. They are the low-density basins of the universe, the places matter left behind while gathering into the bright structures we are more likely to photograph and admire. There is a good reason photographs tend to focus on the bright parts. Galaxies are beautiful. Clusters are spectacular. Filaments, when mapped, show the universe's skeleton in a way that feels almost designed, though it is not designed in any ordinary sense. But voids are harder to appreciate because they are defined by absence. They are places where there is much less to see. A photograph of a void may not look dramatic at first. It may simply look dark, sparse, and quiet. The drama is in the scale. The emptiness is not small. It is not a gap between two stars. It is a region that can stretch across tens or hundreds of millions of light years, with very few galaxies inside. One of the most famous examples is the Bhuta's Void, sometimes called the Great Nothing, which is a name that sounds like it belongs equally to astronomy and to a very tired person staring into the fridge at midnight. This void is a huge, underdense region in the direction of the constellation Bhutas. It is not completely empty, but it contains far fewer galaxies than would be expected for such a large volume of space. The numbers vary with surveys and definitions because cosmic structures do not have tidy walls, but the general point is clear. It is an enormous region where galaxies are unusually scarce. If the Milky Way were located near the centre of such a void, our view of the nearby universe might have been very different. Early astronomers might have seen far fewer galaxies around us, and the discovery of the wider universe could have been delayed or felt even more unsettling. Imagine living in a galaxy inside a deep void. Your night sky would still contain stars from your own galaxy, so it would not look empty in the everyday sense. If you lived on a planet like Earth inside a spiral galaxy, you might still see a Milky Way-like band across the sky. You might still have nearby stars, planets, nebulae, and star clusters. But when your astronomers built telescopes and looked beyond the edge of your galaxy, the surrounding universe would seem lonelier. There would be fewer neighbouring galaxies, fewer bright companions, fewer obvious clusters. The wider cosmos might appear much emptier for a long time, simply because your region of space really was less populated. Your idea of what is normal would be shaped by your address. That is one of the quiet lessons of cosmic voids. Location matters. We do not observe the universe from some perfect central viewing platform. We observe it from inside one galaxy, in one group, in one part of the cosmic web. Our surroundings influence what we first notice. Fortunately, modern surveys look across huge areas and great distances, allowing astronomers to map the distribution of galaxies and see the larger pattern. When enough galaxies are measured, the web appears, the voids appear. The universe stops looking like a random sprinkle and starts looking like a structure with dense and empty regions woven together. The word woven can be useful, as long as we keep it practical. The cosmic web is not made of threads in the usual sense. It is made of matter distributed unevenly through space, shaped by gravity and dark matter. Dark matter plays a major role because it provides much of the gravitational scaffolding. Galaxies form where normal matter falls into dark matter structures. Filaments trace these dense regions. Voids form where density is low. We cannot see dark matter directly with ordinary light, but we can infer its presence from its gravitational effects. Without it, the web would not look the way it does. The visible galaxies are like lights marking a much larger invisible framework. In that sense, voids are not truly empty of dark matter either. They are underdense in dark matter too, but they still contain some. They are not holes in space-time. They are regions where the average density is lower than elsewhere. This difference matters because a void is not a place where physics stops. Gravity still operates there. Light travels through it. Space expands there. Particles pass through it. A galaxy inside a void still has stars that orbit, gas that can form new stars, and dark matter holding it together. The void is not a dead zone. It is a quieter environment. Void galaxies are especially interesting because they grow in relative isolation. A galaxy in a dense cluster may experience frequent interactions, tidal forces, gas stripping, mergers, and pressure from hot cluster gas. A galaxy in a void may have a calmer life, with fewer close encounters. This can affect its shape, star formation, and evolution. Some void galaxies are small, blue, and still forming stars. Others may have developed differently from similar galaxies in denser regions. By studying them, astronomers can ask how much a galaxy's life depends on its environment. Does a galaxy grow differently when it lives in a crowded city compared with a quiet, rural region of the cosmos? The answer appears to be yes, though, as usual, the universe provides details complicated enough to keep researchers awake, which is ironic for our purposes. A void can also help test cosmology. Because voids are large and relatively simple under dense regions, their shapes, sizes, and distribution can tell scientists about gravity, dark matter, and dark energy. The way voids grow depends on how matter clumps and how the expansion of the universe behaves over time. If dark energy changes the expansion rate, that can influence the growth of structure and the size of voids. If gravity behaved differently on large scales, voids might show it. So these empty regions are not just empty scenery, they are scientific tools. The quietest parts of the universe can be some of the most informative. There is something pleasing about that. Humans often focus on bright, busy, dramatic things, and understandably so. A galaxy collision looks spectacular. A supernova is dramatic. A black hole, accretion disk, has strong visual appeal, assuming you're not too close to it. But voids teach us that absence can also carry information. The lack of galaxies is itself a measurement. The shape of a low-density region tells a story. The empty-looking spaces help reveal the rules that built the brighter structures around them. If we move from the local group outward into the wider universe, we would eventually find that galaxy groups and clusters are arranged around these voids. The local group itself is not inside one of the great giant voids, but it does sit in a larger cosmic environment with nearby structures and underdense regions. Around us, galaxies are not evenly spread. There are sheets, groups, clusters, and flows. Our local region participates in the larger web. The Milky Way is not simply floating in a blank sea with Andromeda and a few companions. It is part of a greater arrangement of matter, one that extends far beyond what the eye can see. On maps of galaxy surveys, voids can look like dark bubbles between bright strands. These maps are created by measuring the positions and redshifts of many galaxies, turning points of light into a three-dimensional distribution. The result is often startling. Galaxies form long chains and walls around empty regions. It almost looks biological, like cells under a microscope, or like foam, with galaxies along the surfaces of bubbles. This is not because the universe is a living thing in any literal sense. It is because gravity acting on tiny early density variations naturally produces a web-like pattern. Still, it is hard not to feel that the universe has a talent for making structure at every scale, from snowflakes to spiral galaxies to filaments hundreds of millions of light-years long. The scale of voids is what makes them difficult to imagine. The Milky Way is already about 100,000 light-years across. The distance to Andromeda is about 2.5 million light-years. A large void can be tens of millions of light-years across, and the largest known underdense regions can reach hundreds of millions of light-years in scale, depending on how they are defined. That means a void can be large enough to contain many Milky Way to Andromeda distances across its width. Imagine taking the already impossible gap between our galaxy and Andromeda, then placing that gap again and again and again through a region with very few galaxies. At that point, even the mind's usual emergency backup comparisons begin to fail. You can compare a galaxy to a city, a cluster to a country, a filament to a highway, but a void becomes something like a whole map with almost all the lights removed, and yet a void is not outside the universe. It is not a separate place beyond the cosmic web. It is inside the web, shaped by the same processes, expanding with the same space-time, crossed by the same light. If a beam of light from a distant galaxy travels through a void on its way to us, it may pass through a region with very little matter to interrupt it. That can affect what we see in subtle ways. Voids also influence the motion of matter around them. In a sense, matter flows away from void interiors toward denser boundaries, not because the void is pushing in a magical way, but because gravity pulls matter more strongly toward the surrounding dense regions. The result is that voids can expand relative to the web around them as structure develops. This gives voids a kind of quiet motion. They are not static holes. They change as the universe evolves. Their boundaries shift. Their internal density changes. They can merge with neighbouring underdense regions. The cosmic web becomes more pronounced over time as gravity continues to amplify contrast. Dense regions become denser. Empty regions become emptier. The difference between bright strands and dark gaps grows stronger. The universe develops texture. For life, voids raise an interesting question. If galaxies are rarer there, are habitable planets rarer too? Probably, simply because there are fewer galaxies and fewer stars in a given volume. But a galaxy inside a void can still form stars and planets. There is nothing about a void that prevents a planet from existing inside a galaxy. The larger environment may be quieter, but the local conditions inside a galaxy still matter most for planets and life. A world in a void galaxy could have oceans, weather, mountains, chemistry, and perhaps living things, all while the larger universe beyond its galaxy appears unusually empty. If intelligent observers arose there, their cosmic loneliness might be built into their astronomy from the beginning. That idea has a soft, strange feeling to it. We often wonder whether we're alone in the universe, but a civilization in a void might feel that question more sharply when looking beyond its own galaxy. The night sky inside the galaxy might be rich, but the deep extragalactic sky could seem sparse. Fewer neighbouring galaxies would be visible. Fewer cosmic landmarks would stand nearby. Their first maps of the universe might be maps of absence, and yet, with enough time and sensitive instruments, they too would find the broader web, distant filaments beyond the void, clusters gathered at its edges, and light arriving from far away. Even from a lonely address, the universe would eventually reveal that the loneliness was local. The great voids also help us understand why the universe is not organized, like a simple hierarchy of objects sitting inside objects. Planets orbit stars. Stars belong to galaxies. Galaxies belong to groups and clusters. That part sounds tidy. But then the large-scale structure becomes more like a network. Groups and clusters connect along filaments. Filaments surround voids. Voids fill much of the volume. The universe is not a set of nested boxes. It is a web with dense knots and wide openings. If you only list the bright objects, you miss the architecture. The voids are part of the architecture. This becomes important when we ask how far apart galaxies really are. In dense regions, galaxies may have many neighbours. In voids, a galaxy may be extremely isolated, so there is no single typical distance that captures the whole universe. Environment matters. A galaxy in a rich cluster may have many nearby companions, though still separated by large distances compared with its own size. A galaxy in a void may be tens of millions of light-years from another comparable galaxy. The universe contains crowded regions and lonely regions, and both are real. That variety should make us cautious whenever we picture the cosmos as evenly filled. It is not evenly filled at the scales where galaxies live. It has neighbourhoods, highways, intersections, empty stretches, and enormous quiet zones. The local group is one small neighbourhood. Galaxy clusters are larger crowded cities. Filaments are the roads and bridges, although made by gravity rather than asphalt, which is good because road maintenance on a 100 million light-year filament would be challenging. Voids are the spaces between the roads, huge regions where the map is mostly blank. There is a restful way to hold this idea. The universe is not crowded everywhere. It has room. More room than we can picture. More room than light can cross quickly. More room than galaxies can fill. The great voids are reminders that cosmic distance is not only about how far one bright thing is from another. It is also about the stretches where almost no bright things exist at all. They are the long pauses in the universe's arrangement, not pauses in time, not silences with no meaning, but low-density regions that give the cosmic web its shape. As we think about the distance between galaxies, voids are perhaps the strongest correction to the simple telescope image. A deep image may look packed with galaxies because we are looking through a long column of space, but when we map those galaxies in 3 dimensions, we see that many are arranged around vast, empty regions. The sky may appear full because depth stacks light into one view. The real structure includes immense gaps. What looks crowded from one angle can be mostly empty when unfolded into space. So the great voids where almost nothing lives are not merely curiosities. They are essential to the scale of the universe. They show us that galaxies are not just separated by distances, but sorted by a web of matter and absence. They show us that the darkness between galaxies can widen into regions so large that even whole galaxy groups would seem small beside them. They show us that emptiness itself has structure, and that the universe is shaped as much by what is missing as by what shines. The moment we add expansion to the picture, cosmic distance stops behaving like the kind of distance we use in everyday life. A road between two towns may be long, but the road does not usually stretch while you're driving on it. A hallway may be dark, but it does not quietly become longer while you're walking toward the door, unless you are having a very unusual dream or staying in a hotel with extremely confusing carpets. In the universe, though, on the larger scales, the space between distant galaxies is not fixed like a ruler laid across a table. It changes, it grows, and that means distance between galaxies is not only enormous, but also active in a way that feels deeply unfamiliar. This is where the comfortable idea of a map begins to fail. On Earth, a map is useful because distances stay mostly the same. London and Paris do not drift apart by a noticeable amount while you're making tea. Mountains move slowly with plate tectonics, but not enough to ruin your holiday plans between breakfast and lunch. If a town is 100 kilometers away, you can plan around that. If you travel at a certain speed, you can estimate when you will arrive. The ground beneath the journey is stable enough that distance behaves like a simple quantity. But between very distant galaxies, the ground of the journey is space itself, and space is expanding. To be careful, this expansion does not mean galaxies are flying outward from a central explosion through pre-existing emptiness. That is a common image, and it is understandable, but it is not quite right. The Big Bang was not an explosion in space from one central point. It was an expansion of space everywhere. There is no special center that all galaxies are racing away from. Instead, on large enough scales, the distance between galaxy groups grows because the fabric of space itself expands. Every observer in a typical distant galaxy would see other faraway galaxies receding in much the same way. Everyone can feel like they are at the center, not because everyone is special in the cartographic sense, but because expansion happens throughout space. The usual classroom image is a balloon with dots drawn on its surface. As the balloon inflates, the dots move farther apart. The dots are not crawling across the rubber, the surface between them is stretching. This analogy helps, as long as we remember that the universe is not the surface of a balloon floating inside a larger room, and there is no need to imagine a giant cosmic person inflating it, which would raise several follow-up questions and probably require a very large pump. The useful part is simply this. Distant galaxies can become farther apart because the space between them grows. A different image is raisin bread. Imagine raisins embedded in dough as it rises. Each raisin sees other raisins moving away as the dough expands. Raisins farther away recede faster because there is more expanding dough between them. Again, not perfect, because galaxies are not raisins, though some elliptical galaxies do have a slightly raisin-like commitment to being round and quiet. But the idea helps. The farther away a galaxy is, the more expanding space lies between it and us, and the more that expansion affects the distance. This is the basis of Hubble's law, or more fully the Hubble-Lemaitre law. On large scales, more distant galaxies tend to recede faster, not because they have engines, not because Earth is repelling them, which would be rude. They recede because the space between distant unbound galaxies is expanding. If a galaxy is twice as far away, then there is roughly twice as much expanding space between us and it, so its recession speed due to expansion is greater. This relationship is one of the pillars of modern cosmology. It tells us that the universe is not static, it is changing as a whole. But here is where things become strange. If space expands while light is travelling through it, then the light itself is stretched. Light travels as waves, and as the universe expands, the wavelength of that light can be stretched to longer wavelengths. Longer wavelengths of visible light are redder, so this stretching is called redshift. For very distant galaxies, the redshift can be large enough that light originally emitted in visible or ultraviolet wavelengths arrives to us in infrared. This is one reason infrared telescopes are so important for studying the early universe. They are not just looking through dust. They are catching ancient light that has been stretched by cosmic expansion during its long journey. Redshift is not simply a colour change in the decorative sense. It is a measurement of how much the universe has expanded since the light was emitted. If a galaxy's light is highly redshifted, that means the light has travelled across a universe that has changed significantly during the journey. The galaxy was not merely sitting far away in a static space, while photons obediently crossed the gap. The gap itself was growing. The light was being stretched while it travelled. The distance between here and there was not just large, it was evolving. This is one of the reasons distance in cosmology has more than one meaning. In everyday life, we usually expect one distance to be enough. How far is the shop? How far is the station? How far is the bed? And is it socially acceptable to crawl there at 8:30 p.m? But in cosmology, astronomers use different kinds of distance depending on the question. There is look-back time, which tells us how long the light has been travelling. There is proper distance, which can mean the distance to an object at a particular cosmic time. There is co-moving distance, which factors out the expansion and lets us describe positions in a coordinate system that expands along with the universe. There is luminosity distance, tied to how faint an object appears. There is angular diameter distance, tied to how large an object appears on the sky. These are not invented to make life difficult, although it may feel that way during a cosmology lecture. They exist because expansion makes "how far away is it?" a more complicated question than it sounds. Take a distant galaxy whose light has been travelling for 10 billion years. You might be tempted to say it is 10 billion light years away. That is a reasonable first thought, because a light year is the distance light travels in 1 year. But because space expanded while the light was travelling, the galaxy is now much farther away than 10 billion light years in the usual present-day distance sense. The light took 10 billion years to reach us, but during those 10 billion years the space between us and the galaxy grew, so the object's current distance may be far larger than the light travel time alone suggests. This is where the brain begins to quietly put on a dressing gown and say, "I was not trained for this." The observable universe is a good example. The universe is about 13.8 billion years old, so one might expect the farthest observable things to be about 13.8 billion light years away. But because space has expanded while their light was travelling, the radius of the observable universe is much larger, about 46 billion light years in current comoving distance. That does not mean light travelled faster than light. It means the distance to the regions that emitted the light has grown while the light was on its way. No photon broke the speed limit. The ruler changed length. That phrase, "the ruler changed length," is not perfect, but it helps. In cosmology, the scale of space itself changes with time. If two distant galaxies are not gravitationally bound together, the distance between them can increase as the universe expands. The galaxies may be nearly at rest relative to their local surrounding space, yet the separation grows because the space between them grows. This can lead to another strange result. Very distant galaxies can recede from us faster than the speed of light. This does not violate special relativity, because they are not moving through local space faster than light. Instead, the space between us and them is expanding. Special relativity limits motion through space locally. Cosmic expansion over vast distances is a general relativistic effect. That is not a loophole in the rules. It is part of the rules when the universe itself is involved. This is why some galaxies are visible to us even though their present recession speed may be greater than light speed, while other galaxies may eventually become unreachable even by light we send today. The universe has horizons. There are limits to what can influence what, because light has finite speed and space is expanding. Some light emitted long ago by very distant galaxies can reach us now because, when it began the journey, the conditions allowed it to make progress through the expanding universe. But light emitted today from the same galaxy may never reach us if the expansion carries that galaxy's region away too quickly. The universe is not only large, it has changing access rules. That idea can sound lonely, but it is also part of the structure of reality. There are galaxies whose ancient light we can see, while their present state is forever beyond direct observation. We see what they were not what they are now. For nearby galaxies, the delay may be millions of years. For very distant galaxies, it may be billions. For the farthest observable light, we are seeing back toward the early universe itself. Cosmic expansion turns astronomy into a study of both distance and history, but it also places limits on the future. Some regions will drift beyond our ability to ever exchange signals, not because they vanish, but because the expansion between us and them becomes too great. This changes how we think about the phrase, the distance between galaxies. Between nearby galaxies inside a gravitationally bound group, expansion may not matter much. The Milky Way and Andromeda are not being pulled apart by the expansion of the universe. They are part of the local group, where gravity dominates. The space between them is enormous, but it is not expanding in the same simple Hubble flow way as the space between distant galaxy groups. Their mutual gravity, along with the influence of other local group members, shapes their motion. That is why Andromeda can approach us even while faraway galaxies generally recede. Inside galaxies, expansion does not stretch star systems apart. The solar system is not expanding. Earth is not expanding away from the sun because of cosmic expansion. Your bedroom is not expanding away from your kitchen, though it may feel that way if you're very tired and need water at night. Bound systems hold together. Gravity, electromagnetic forces, and other local interactions overwhelm cosmic expansion at small scales. The expansion of the universe becomes important when we look at large, unbound distances between galaxy groups and clusters. This scale dependence is important. Expansion is not a force pulling everything apart everywhere. It is not stretching your body, your house, or the Milky Way. It is a property of the large-scale universe. On small scales, matter is clumped into bound systems. On large scales, those systems separate as space expands. So the universe is a mixture of stability and growth. Galaxies remain galaxies. Clusters remain bound where gravity is strong enough. But the vast distances between unbound structures grow. Then there is the extra twist that the expansion is accelerating. Observations of distant Type Ia supernova in the late 1990s show that the expansion of the universe is not merely continuing, but speeding up over cosmic time. The cause is usually called dark energy, a name that is accurate in the sense that it is dark and related to energy, but also wonderfully unhelpful if you are hoping for a tidy explanation. Dark energy appears to make up most of the energy content of the universe, and it affects the expansion on the largest scales. We do not yet know exactly what it is. It may be related to the cosmological constant, an energy of empty space itself, or it may point to deeper physics still unknown. Either way, it makes cosmic distance even stranger because the gaps between distant galaxy systems do not just grow, their growth accelerates. Acceleration means the future universe will look different. Over very long times, distant galaxies outside our gravitationally bound neighborhood will move farther away. Their light will become increasingly red-shifted and harder to detect. Eventually, many galaxies beyond our local region may fade from view, not because they stop existing, but because their light can no longer reach us in a useful way or become stretched beyond detection. Future astronomers in the far future, if any exist, may see a much emptier observable sky beyond the merged remains of the local group. They may not easily know that the universe once contained a vast cosmic web of galaxies visible across deep time. Their local view could become more isolated. There is something unsettling about that, but also clarifying. We live at a cosmic time when the universe is old enough to contain galaxies, stars, planets, heavy elements, and curious observers, but young enough that distant galaxies are still visible. The night sky and our telescopes give us access to a broad cosmic history. We can see nearby galaxies in their more recent forms and faraway galaxies as they were long ago. We can measure redshifts and reconstruct expansion. We can study the cosmic microwave background, the afterglow of the early universe. We live during a window when the universe has made itself readable. Expanding space also changes the meaning of speed. In ordinary travel, speed tells you how quickly you're crossing a fixed distance. Drive at 100 km per hour for 2 hours and you cover about 200 kilometers, assuming traffic, weather and snack breaks behave themselves. But for light crossing cosmological distances, the distance itself changes during the journey. A photon may be moving locally at the speed of light at every moment, but the total distance to its source can increase while it travels. Sometimes the source was closer when the light was emitted, much farther by the time the light arrives, and farther still now in a present-day cosmological model. So a simple travel story becomes a space-time story. This is also why asking where a distant galaxy is now becomes tricky. In everyday life, now feels straightforward. What is the moon doing now? What is your friend doing now? What is the cat doing now? And should someone be worried about that noise? But in relativity, there is no universal present moment shared across the entire cosmos in the simple way we imagine. For distant galaxies, especially across billions of light years, now depends on how we define a cosmic time coordinate. Cosmologists can define a useful shared time based on the large-scale expansion of the universe, but that is not the same as the intuitive now we use in daily conversation. The farther away the galaxy, the more careful the word becomes. Even without going too deep into relativity, the practical point is clear. We see distant galaxies as they were when their light left. Their current state, according to a chosen cosmological model, may be very different. They may have merged, changed shape, formed new generations of stars or stopped forming stars. Some stars we see in them may no longer exist. Some planets may have formed after the light began travelling. The image is real, but it is not current in the everyday sense. Expanding space adds another layer. The distance to that galaxy has changed during the light's journey. So the image is not just old. It has arrived across a changing universe. The stretching of light gives us evidence for that change. When astronomers measure redshift, they are reading expansion from the light itself. Spectral lines from known elements appear at longer wavelengths than they would in a laboratory. Hydrogen, oxygen, calcium and other elements leave identifiable fingerprints, but those fingerprints are shifted. The amount of shift tells us how much the light has been stretched. For nearby objects, motion can complicate things. For distant galaxies, cosmological redshift becomes one of our main guides. It lets us place galaxies in cosmic history and understand how the universe has expanded since the light was emitted. Because of this, distance and age become connected in a way that is not true on Earth. A faraway galaxy is not simply far away. It is also seen at an earlier stage of cosmic history. A galaxy with high redshift is not just distant in space, it is young in the image we receive. When telescopes observe very high redshift galaxies, they are looking at systems that existed when the universe was much younger. This allows astronomers to study how galaxies formed and grew. The expansion that makes distance strange also gives us a time machine, limited but powerful. It spreads cosmic history across the sky. There is a quiet trade here. Expansion makes direct contact harder, creates horizons, stretches light, complicates distance, and eventually hides distant galaxies. But expansion also leaves measurable marks. It gives redshift meaning. It lets us infer the history of cosmic growth. It makes the large-scale universe dynamic rather than frozen. Without expansion, the universe would be a very different place, and our methods for understanding its history would be different as well. The same effect that separates galaxies also helps us read the story of their separation. A useful way to hold this is to imagine the universe not as a map printed once, but as a map whose scale changes over time. The dots representing galaxy groups may stay in roughly the same co-moving positions, but the scale between them grows. If you measured with a ruler that expanded with the map, the coordinates might remain steady. If you measured with a ruler that did not expand, the distances would increase. Cosmologists use these different ways of measuring because each is useful for different questions. Are we asking how long light travelled, how far the galaxy is now, how bright it appears, how large it looks, how much space has expanded? There is no single answer that serves every purpose. This can be frustrating, but it is also a sign that the universe is richer than our first questions. When a child asks, "How far away is that galaxy?" the honest answer may begin with a number, but the fuller answer must ask, what kind of distance do we mean? The distance when the light was emitted? The distance the light travelled? The distance now in an expanding universe? The distance inferred from brightness? The distance related to apparent size? Each answer tells a different part of the truth. The universe is not being evasive, it is being relativistic, which is a kind of evasive behaviour with equations. For our purpose tonight, the simplest lesson is that expanding space makes galaxy distances more than gaps between objects. Those gaps have histories. They change while light crosses them. They're affected by gravity, dark energy, and the overall evolution of the universe. Nearby bound galaxies live in local gravitational neighbourhoods. Faraway galaxies participate in the wider expansion. The farther out we look, the more distance becomes tied to time, redshift, and the changing scale of space itself. So when we think about the distance between galaxies, we should not picture fixed islands sitting in a static ocean. That picture helped us at the beginning, but now it needs to grow. The ocean itself can expand. The waves of light crossing it can stretch. The shores can recede not because they are sailing away through water, but because the water between them is increasing. And if the ocean is big enough, some shores may eventually pass beyond our ability to ever reach or see them clearly again. This does not make the universe less understandable. It makes it more careful. It asks us to choose our words, define our distances, and remember that intuition built on Earth may not be prepared for cosmic scales. The distance between galaxies is impossible to imagine, partly because it is large, but also because it is not still. It is written into a universe that has been expanding for billions of years, a universe where light is stretched, where faraway views are old, where the future visibility of galaxies depends on the changing behaviour of space itself. What begins as empty space eventually becomes evidence. That is one of the quiet surprises hidden between galaxies. At first, the gaps seem like the parts of the picture where nothing is happening. The stars shine, the galaxies glow, the clusters gather, the filaments stretch across the dark, and between them, there are regions that seem to be only absence, only distance, only the long unlit spaces that make the bright things look bright. But when astronomers measure those gaps carefully, they discover that the spaces between galaxies are not just leftover room. They are records. They tell us how matter gathered, how gravity worked, how the universe expanded, and how small early differences became the enormous cosmic web we see today. This is a very different way of thinking about emptiness. In daily life, an empty space usually means a space waiting to be filled. An empty chair, an empty cup, an empty biscuit tin, which is often the most emotionally complicated kind of emptiness. We treat the empty part as less important than the object. But in the universe, the gaps are not merely missing objects. They help define the whole arrangement. The distances between galaxies show where matter did not collect. The voids show where gravity slowly pulled material away toward denser regions. The filaments show where matter gathered and flowed. The clusters show where that gathering became strongest. To understand the bright structures, we have to understand the dark spaces around them. Think again of the cosmic web. Galaxies are not spread randomly across the universe. On the larger scales, they form a network of dense knots, long filaments, wide sheets, and underdense voids. This structure did not appear all at once. It grew from tiny density variations in the early universe. Some places had slightly more matter than average. Some places had slightly less. The differences were extremely small at first, but gravity is patient. Over billions of years, the slightly denser regions pulled in more matter. That made them denser still. The slightly emptier regions lost matter to the surroundings and became emptier. A tiny unevenness became a huge pattern. So the gap between galaxies tells us something about the beginning. It tells us that the early universe was not perfectly smooth. It was close to smooth, but not perfectly. If it had been perfectly uniform, matter might not have clumped into stars, galaxies, clusters, and filaments in the way we see. There would have been no preferred places for gravity to start building structure. But because there were small variations, structure could grow. Every galaxy cluster, every filament, every void is connected to those early variations. When we map where galaxies are and where they are not, we are indirectly reading the ancient pattern that gravity amplified. That is a strange thought, but a practical one. The gaps are not random. Their sizes, shapes, and locations are clues to the conditions of the young universe. If the early universe had different ingredients, if dark matter behaved differently, if gravity worked differently, if dark energy had a different effect, the cosmic web would not look exactly the same. Voids might be larger or smaller, filaments might form differently, clusters might be more common or less common. The spacing of galaxies carries information about the rules that shaped everything. Dark matter is a major part of that story. We cannot see dark matter directly with ordinary light. It does not shine, reflect, or absorb light in the familiar ways, but it has gravity. It helps pull matter into structures. Galaxies form inside dark matter halos, and the larger cosmic web is strongly shaped by dark matter's distribution. In a sense, visible galaxies are like lamps placed along an invisible framework. The lamps do not show every part of the framework, but they trace enough of it for astronomers to infer the shape. When we map the gaps between galaxies, we're also mapping the underlying dark matter structure, not perfectly, but meaningfully. This is one reason large galaxy surveys matter so much. A single galaxy is interesting. A cluster of galaxies is more informative, but millions or billions of galaxy positions create a map of the universe's large-scale pattern. Astronomers measure where galaxies appear in the sky and how far away they are, often using redshift. Once enough positions are known, the web emerges from the data. It becomes possible to see the filaments, identify voids, and study how the pattern changes with distance, which also means studying how it changed over time. The farther away we look, the earlier the stage of cosmic history we're seeing. Large surveys are a little like making a map of a country at night by recording every visible town light from far above. One light tells you a town exists. Many lights reveal roads, cities, coastlines, and empty regions. With enough lights, the pattern becomes geography. With enough galaxies, the pattern becomes cosmology. The gaps are part of that map. If there is a huge dark region with very few galaxies, that is not just a lack of data, assuming the survey is complete enough. It may be a real cosmic void. If galaxies line up in long strands around it, that tells us how matter has collected. The absence becomes measurable. Some of the most valuable information comes from a pattern called baryon acoustic oscillations. The name sounds technical because it is, and also because cosmology has never been especially worried about sounding cozy. But the basic idea can be explained gently. In the early universe, before atoms formed, matter and radiation were mixed in a hot, dense plasma. Pressure waves moved through that plasma, a bit like sound waves. Later, when the universe cooled enough for light to travel freely, those waves left a faint preferred scale in the distribution of matter. Billions of years later, that scale can still be detected in the way galaxies are spaced. It is not a perfect ring around every galaxy that you can see with your eyes. It is a statistical pattern, visible when many galaxies are measured together. This pattern acts like a cosmic ruler. Because the size of that early imprint is understood, Astronomers can compare how large it appears at different distances and use it to study the expansion of the universe. The gaps between galaxies, when measured in huge numbers, preserve the echo of ancient waves. That is a wonderfully concrete fact. The universe once had pressure waves moving through its early plasma, and today the distribution of galaxies still carries a trace of them. The spaces between galaxies are not just spaces, they are marked by old physics. This is one way the gaps teach us about dark energy. Dark energy is the name given to whatever is driving the accelerated expansion of the universe. We know the expansion is speeding up from multiple lines of evidence, including observations of distant supernovae and the large-scale distribution of galaxies. But what dark energy actually is remains one of the major open questions in physics. By measuring galaxy spacing at different cosmic times, astronomers can track how expansion has changed. If the expansion history matches one model, that tells us one thing. If it deviates, that could point to new physics. The pattern between galaxies becomes a way of testing the behavior of the whole universe. Voids also help with this. Because they are under-dense regions, their growth depends on gravity and expansion. Matter tends to flow away from void interiors toward denser walls and filaments. As the universe expands and structure grows, voids change. Their shapes and sizes can provide clues about cosmological parameters. They can also help test whether gravity behaves as expected on very large scales. A void may look like a quiet place where not much happens, but its emptiness has a measurable shape, and that shape depends on the history of cosmic growth. There is a good lesson here about science in general. Sometimes the thing you cannot see directly can be studied by its effects. Dark matter is inferred through gravity. Dark energy is inferred through expansion. The early universe is inferred through relic patterns and ancient light. The gaps between galaxies become useful because they show the effects of all these invisible or distant processes. We do not have to touch the universe's ingredients directly to learn about them. We can study how they arrange what we do see. The gaps also tell us about galaxy evolution. A galaxy in a dense region has a different life from a galaxy in a sparse region. In a cluster, galaxies can interact frequently. They can pass near one another, pull on one another, strip gas from one another, and merge. The hot gas in clusters can remove gas from galaxies as they move through it, shutting down star formation in some cases. A galaxy in a void may have fewer close encounters and a quieter history. It may keep more of its gas and continue forming stars differently. Environment matters. The distance to other galaxies affects a galaxy's development. This means the empty spaces are not passive. They shape what galaxies become by creating different conditions. A galaxy with many neighbours lives in a busy gravitational environment. A galaxy with few neighbours evolves more independently. The gap around a galaxy can influence how often it collides, how much gas it keeps, how its star formation changes, and whether it becomes distorted or remains relatively undisturbed. The spaces between galaxies are part of each galaxy's biography. Our own Milky Way is shaped by its environment too. It has satellite galaxies. It has absorbed smaller systems. It is part of the local group. It is not in a rich cluster, where life for a spiral galaxy might be much more disruptive. The distance to Andromeda, to Triangulum, to the Magellanic Clouds, and to smaller dwarfs all belongs to the Milky Way's story. If our galaxy had formed in a denser region, its history could have been different. Perhaps more mergers, perhaps a different shape, perhaps a different rate of star formation. The gap around us helped make home what it is. This matters for planets and life as well, though carefully. The large-scale environment does not decide everything about a planet. Local conditions around a star matter enormously. But a galaxy's history affects the availability of heavy elements, the rate of star formation, the frequency of disruptive events, and the long-term stability of stellar neighborhoods. If galaxy environments influence galaxy histories, then the gaps between galaxies are indirectly connected to the kinds of stars and planets that form. The distance between galaxies may seem remote from a quiet bedroom on Earth, but it belongs to the chain of circumstances that made galaxies like the Milky Way possible. The gaps also tell us that the universe has no obvious centre or edge in the part we can observe. When galaxies are mapped on large scales, the same web-like structure appears in different directions. There are local variations, of course. Some regions are denser, some emptier, but on the larger scales, the universe appears broadly homogeneous and isotropic, meaning it looks statistically similar in different places and directions. This does not mean every region is identical. It means that if you zoom out far enough, the overall pattern becomes consistent. The gaps and clusters average into a cosmic structure that supports the idea that we do not occupy a special central location. That is another humbling message from the spaces between galaxies. The Milky Way is not the centre of the cosmic web. The local group is not the grand hub of creation. We live in one region among many. Our surroundings are meaningful to us, but not cosmically privileged in the old-fashioned sense. The gaps help reveal that by showing the same kinds of structures elsewhere. Voids, filaments, clusters, groups, and walls appear across the observable universe. The pattern is not arranged around us. We're inside it. There is comfort in that, if we let it be comfort. Not being central does not mean being unimportant. It means we belong to a larger order that does not require us to be the focus. A star does not need to be central to shine. A planet does not need to be large to matter to the life on it. A human thought does not need to span the universe to be real. The gaps between galaxies remind us that the universe is built on scales beyond our purposes, but we are still part of it. The calcium in our bones, the oxygen we breathe, the iron in our blood, all came from stars and galaxies shaped by the same cosmic history. Another thing the gaps tell us is that the universe has changed over time. Nearby galaxy maps show the more recent cosmic web. Distant surveys show earlier versions. Because light takes time to reach us, looking farther away means looking further back. Astronomers can compare the clustering of galaxies at different distances to study how structure grew. Were galaxies more clumped at one time? How quickly did clusters form? How did voids expand? How did dark matter halos assemble? The gaps between galaxies at different cosmic ages help answer these questions. This is why future and current surveys are so ambitious. They are not merely collecting pretty images, though many images are very pretty and deserve a respectful pause. They are measuring positions, redshifts, shapes, and weak gravitational lensing signals across enormous numbers of galaxies. Weak lensing is especially useful because it reveals how mass bends light, including mass we cannot see. By studying tiny distortions in the shapes of distant galaxies, astronomers can map the distribution of matter between us and them. That includes dark matter, so even the gaps can be weighed, in a sense, by how they and the structures around them bend background light. Weak lensing turns the universe into a lensing field. Massive structures slightly distort the images of more distant galaxies. The effect is tiny for individual galaxies, but across large numbers the pattern becomes measurable. This lets scientists map matter directly in a way that does not rely only on where visible galaxies are. That is important because galaxies are biased tracers of matter. They form in certain places, especially in dark matter halos, but they do not mark every bit of mass. Lensing helps reveal the fuller distribution. The gaps between galaxies may contain little visible matter, but their gravitational influence, or lack of it, still contributes to the map. There are also gas clues. The space between galaxies can contain extremely thin gas, sometimes detected through absorption lines in the spectra of distant quasars. This gas can trace the cosmic web in a faint way. Some of the ordinary matter in the universe is not inside stars or galaxies, but spread through intergalactic space, warm or hot, thin and difficult to detect. The gaps may hold some of the missing ordinary matter that astronomers have worked to account for. Again, empty does not mean nothing, it means low density, and low density can still matter when the volume is huge. The huge volume is the key. A region between galaxies may contain very few particles per cubic meter, far less than any vacuum we normally imagine. But if that region stretches for millions of light years, the total amount of matter can still be significant. Space is very good at making tiny densities add up over large distances. This is why astronomers must think in both density and volume. A room with 1 grain of dust is almost clean. A universe-sized region with 1 grain of dust per room-sized volume contains a very large amount of dust, and possibly a very irritated cleaner. The gaps also reveal the limits of our measurements. We know a great deal, but not everything. Some distant galaxies are too faint to observe easily. Some low-surface brightness galaxies may be missed. Some voids may appear emptier than they are because our surveys are incomplete. Dust, instrument limits, selection effects, and model assumptions all matter. Good astronomy does not ignore these problems. It studies them, corrects for them, and uses different methods to cross-check. The gaps between galaxies tell us about the universe, but only if we're careful not to confuse what we cannot see with what is not there. This is especially true when mapping faint dwarf galaxies or diffuse structures. The universe contains objects that are easy to miss because they spread their light thinly. A compact bright galaxy may be visible at a great distance, while a nearby diffuse galaxy can hide in plain sight. That means our maps improve as instruments improve. The gaps may shrink slightly in our understanding when we discover faint objects within them, but the large-scale pattern remains. The universe has dense regions and underdense regions, filaments and voids, structure and space. Better data makes the map richer, not simpler. In a deeper sense, the gaps tell us that gravity has been organizing the universe for nearly all of cosmic history. Gravity is slow compared with explosions and human drama, but it is persistent. It takes small irregularities and grows them. It gathers matter into halos. It feeds galaxies along filaments. It builds clusters. It empties voids. It works over billions of years, not minutes. If you want to understand why galaxies are where they are, you have to think like gravity, which is to say, patiently and without concern for appointment times. The spaces between galaxies are also where expansion has its clearest stage. Inside a galaxy, gravity holds stars together. Inside a group, gravity can bind galaxies. But between far apart galaxy systems, expansion dominates. The gaps grow. Light crossing them is redshifted. The pattern of those gaps over time tells us how expansion has changed. This is why distance itself becomes data. A separation is not just a number on a map. It is a result of cosmic history and a clue to cosmic future. That future is written partly in the gaps. If expansion continues accelerating, distant unbound galaxies will move farther away and become harder to see. Galaxy groups like our local group may remain bound, but the wider universe will become increasingly inaccessible. The gaps between large-scale structures will grow. The cosmic web, visible to us now across deep time, may eventually fade from the view of future observers. The gaps are not only records of the past, they are signs of where the universe is going. There is a practical beauty in all this. The dark spaces between galaxies, which first seem like the least interesting parts of the picture, turn out to be some of the most informative. They tell us about initial conditions, dark matter, dark energy, galaxy evolution, gravitational growth, cosmic expansion, and the limits of observation. They show that the universe is not just a collection of shining objects, but a structured whole. The gaps are part of the evidence. The emptiness has content not because it is full, but because its shape, size, and distribution mean something. So when we look at a deep image filled with galaxies, it is worth noticing not only the lights but the intervals. Each dark stretch may represent an enormous physical distance. Each sparse region may belong to a void. Each concentration may mark a filament or cluster. The universe is written in contrast, bright and dark, dense and thin, bound and expanding. seen and inferred. Without the gaps, we would not know the full structure. Without the spaces between galaxies, the galaxies themselves would tell only part of the story. And this brings the subject back to us in a quiet way. The distance between galaxies is impossible to imagine, but it is not impossible to study. The gaps are too large for travel, but not too large for light. They are too empty for ordinary senses, but not too empty for measurement. They are too slow in their changes for a human lifetime, but not too slow for cosmic history. We live in a universe where even absence can be informative, where a dark region can tell us about the earliest ripples in matter, and where the space between galaxies helps explain why there are galaxies at all. By the time the gaps between galaxies begin to feel like evidence instead of blankness, something interesting happens to the mind. The scale has not become smaller, the numbers have not become easier. Andromeda is still millions of light years away. The local group is still spread across a volume so large that even light needs ages to cross it. The great voids are still wider than ordinary imagination can manage. Expanding space still makes distance behave in ways that would make a road map give up and quietly become a napkin. None of that changes, but the feeling can change. The first reaction to such size may be shock or unease, or the sense that we are impossibly small. Then, slowly, if we stay with it, that smallness can become something else, not frightening, not empty, but strangely peaceful. Because being tiny in the universe is not the same as being meaningless. That is an important difference, and one the night sky often teaches gently. A human life is brief compared with the age of the Milky Way. A bedroom is small compared with a galaxy. A planet is tiny beside the local group. Our whole civilization has existed for only a narrow slice of the time it takes light to cross from Andromeda to Earth. Those facts are true. They are not insults. They are measurements. The universe is large and we are small within it, but small things can still matter very much to the small lives that hold them. Think about the way scale works in ordinary life. A single house is tiny compared with a city, but it can contain an entire childhood. A kitchen table is tiny compared with a planet, but it can hold conversations people remember for decades. A cup of tea is tiny compared with an ocean, but if you're cold and tired, the tea matters more than the ocean at that moment. Meaning does not always follow size. If it did, galaxies would be more important than people, and galaxy clusters would be better at making toast, which so far has not been demonstrated. The universe does not become less real because we are small, and we do not become less real because the universe is large. We are simply operating at different scales. Galaxies move over hundreds of millions of years. Stars live and die across millions or billions of years. Planets form from disks of dust and gas, cool, change, and sometimes develop oceans, atmospheres, chemistry, and life. Humans live in days, meals, memories, messages, seasons, and sleep. The fact that our scale is smaller does not make it false. It only tells us where we belong in the larger arrangement. There is comfort in knowing that we do belong. We are not outside the cosmos looking in. We are not separate from the galaxies we study. The matter in our bodies was made in stars and stellar explosions. Hydrogen in our bodies began in the early universe. Carbon, oxygen, nitrogen, calcium, and iron were forged through the lives and deaths of stars. Long before Earth existed, earlier generations of stars made the heavier elements that later became rock, water, air, bone, blood, and brain tissue. So when we look at galaxies across the dark, we are not strangers staring at unrelated lights. We are matter in the universe learning to recognize other places where matter gathered. That may sound grand, but the mechanism is practical. Stars form from gas. Inside stars, nuclear fusion builds heavier elements. Massive stars return material to space through winds and supernova explosions. Some smaller stars shed enriched outer layers late in life. Over time, galaxies recycle this material into new stars, planets, and sometimes living worlds. Our solar system formed from a cloud already enriched by earlier stars. Earth is not made from untouched material. It is made from cosmic leftovers that became a planet. That is not a discouraging origin. Leftovers can be excellent, as anyone who has eaten cold pizza the next morning may quietly confirm. This means the distance between galaxies is not only a measure of separation, it is also part of a larger story of connection. The Milky Way is one galaxy among many, but the physics that shaped it also shaped other galaxies. Gravity gathered matter there as it gathered matter here. Stars formed there as stars formed here. Elements were made there as elements were made here. The galaxies are separated by deep space, but they follow the same natural laws. Their light reaches us, and our instruments can read it. We are physically far from them, but intellectually connected by observation and explanation. That connection is one of the most comforting things science offers. It does not pretend the universe is small. It does not shrink cosmic distance into something convenient. It lets the scale remain honest, and then shows us that honesty does not have to be cold. The Milky Way is enormous. Andromeda is far away. The voids are vast. The observable universe contains more galaxies than any person could count in a lifetime. And still, from this small planet we can measure distances, map structures, study ancient light, and ask reasonable questions. Our bodies are local. Our understanding can travel farther. Of course, our understanding travels in a very specific way. It does not travel like a spaceship. It travels by receiving light, building models, testing ideas, correcting mistakes, and improving instruments. It travels by admitting uncertainty. It travels by noticing that a faint red smudge is not just a smudge, but a galaxy whose light has been stretched by the expansion of space. It travels by turning the darkness between galaxies into data. This kind of travel may be slow and careful, but it is real. It is the mind moving where the body cannot. There is something restful in that, especially at night. We do not have to conquer the distance between galaxies to appreciate it. We do not have to cross the voids to understand that they exist. We do not have to stand outside the Milky Way to know we live inside a vast spiral system. We can lie still, perhaps under a roof, perhaps under a blanket, perhaps with the room mostly dark, and still think our way outward. The body can remain warm and quiet while the mind moves from Earth to the moon to the sun to nearby stars, from nearby stars to the Milky Way, from the Milky Way to Andromeda, and from there to the larger cosmic web. That contrast is gentle. The distances are huge, but the act of considering them can be calm. Nobody is asking you to hold all of it at once. Nobody is asking you to visualize every galaxy, every void, every light year. The mind can approach scale in layers. First, the room, then the town, then the planet, then the solar system, then the galaxy, then the group, then the web. Each step is too large to fully picture, but each step can still be understood in relation to the last. We may not imagine the full distance between galaxies directly, but we can understand why it is beyond imagination. That itself is a kind of understanding. It is also worth remembering that the universe does not feel large to itself. Size is something observers compare. The universe simply is. Galaxies do not sit around feeling distant from one another. A photon crossing space does not become impatient. A void does not feel lonely. These are human reactions, and that is fine. We are human. We bring feeling to measurement. We look at a number like 2.5 million light years and try to translate it into awe, or unease, or wonder, or peace. The number does not require any of those feelings, but we do. Feelings are part of how we meet reality. Sometimes people worry that learning cosmic scale makes human life seem small in a bad way. If galaxies are so far apart, if stars are so many, if the universe is so old, then what are our little concerns? What is a missed train, a late reply, a cluttered room, a bad cup of coffee, compared with 100 billion galaxies? And the answer is simple. Those concerns are small, and they are still yours. Their smallness does not erase them. It can only place them in context. A worry may soften when set beside the local group, not because it is silly, but because the mind is reminded that no single moment has to hold the entire weight of existence. The universe is wide enough to give a little room around the thought. That room can be useful. Cosmic scale can loosen the grip of urgency. The galaxies are not rushing. The Milky Way turns slowly. Andromeda approaches, if its long path brings it that way, over billions of years. Voids grow over cosmic time, light crosses space without complaint. Against that background, the mind may be allowed to slow down, not because human life is unimportant, but because not everything needs to be solved at once. The universe has been unfolding for a very long time. You're allowed to breathe for a moment. There is a practical comfort here too. We live in a stable enough region of the universe to exist at all. Earth orbits a long-lived star. The solar system sits inside the Milky Way, not too close to the crowded galactic centre, not wandering alone between galaxies. Our galaxy belongs to a small group, not the violent heart of a rich cluster where interactions might be more frequent. These conditions are not guarantees of safety, and the universe is never completely risk-free, but they are part of the background that allowed life here to develop. Our smallness is not random emptiness. It is a location within a structure. The gaps between galaxies help protect that structure in a way. They allow galaxies to have their own histories. They keep star systems bound inside galaxies, while larger structures evolve slowly. They make collisions between individual stars rare even when galaxies merge. They give light room to travel and carry information. They give the universe depth, history, and separation. Without distance, the universe would be a very different place. The gaps that seem so impossible are part of the reason galaxies can be galaxies. Stars can form in them, and planets can orbit quietly enough for life to wonder about the gaps. When we look at the night sky, most of the galaxies are invisible to the unaided eye. We see stars in our own Milky Way. Perhaps we see the faint patch of Andromeda. Perhaps from the southern hemisphere, the Magellanic Clouds. Most of the wider cosmic web is hidden from ordinary sight, yet it is there. Telescopes reveal it. Surveys map it. Equations describe its growth. The sky above us is not empty simply because our eyes cannot see everything. Human senses are limited, but they are extendable. A telescope is an extension of the eye. A detector is an extension of sight. Mathematics is an extension of pattern recognition. Science is one of the ways a small creature learns to handle a large universe without pretending it is smaller than it is. And there is another comfort in the fact that we do not see everything at once. Imagine if the full scale of the universe were visible to us every time we looked up. Every galaxy, every void, every distance, every ancient photon, all present in unavoidable detail. It might be too much. Instead, the universe reaches us gradually. A star here, a planet there, a faint galaxy in a telescope, a deep field after long exposure, a redshift measured carefully, a map built from many nights of observation. Knowledge arrives in a form the mind can work with. The universe is enormous, but our understanding can be paced. That pacing matters for this kind of journey as well. We began with the simple fact that galaxies are separated by distances too large to imagine directly. We moved from nearby examples to the space between the Milky Way and Andromeda, from telescope illusions to light as a ruler, from the local group to voids, from expansion to what the gaps reveal. Each step made the universe larger, but also more understandable. The goal was never to make the distance small. The goal was to make the distance meaningful. And perhaps that is the best way to end with cosmic scale. Not by claiming we can truly picture it, but by accepting that understanding is not the same as picturing. You cannot picture 1,000,000 years in the way you can picture a day. You cannot picture 2.5 million light years in the way you can picture a walk down the street. You cannot picture a cosmic void hundreds of millions of light years wide in the way you can picture an empty field. But you can understand what the numbers mean. You can understand that light takes time, that space expands, that galaxies gather along filaments, that voids are under dense regions, that our galaxy belongs to a local group, and that our small planet has a real place inside that structure. That is enough. It is more than enough. The human mind does not need to contain the universe in order to belong to it. A wave does not need to contain the ocean. A leaf does not need to understand the forest to be part of the tree. And a person, resting quietly at the edge of sleep, does not need to imagine every galaxy to feel the calm of knowing they're inside something vast, ordered, changing, and real. So, if tonight's journey has made you feel small, let it be the good kind of small. The kind that takes pressure off the shoulders. The kind that makes the room feel safe and close. The kind that reminds you that your thoughts can rest for a while because the universe is not waiting for you to hold it together. The galaxies will continue moving. Light will continue crossing the dark. Space will continue expanding on the larger scales. The local group will continue its slow gravitational story. The great voids will remain quiet. And here, on this small world, in this brief human moment, you are allowed to be still. Before you drift away, let me ask you again, gently. Where are you listening from tonight? Are you under city lights, under a cloudy sky, near the sea, in a quiet apartment, in a room where the world has finally gone soft around the edges? And when you think about the distance between galaxies now, does it feel frightening, or does it feel peaceful in its own strange way? There is no right answer. The universe is large enough for many feelings. If this quiet voyage through cosmic distance brought you a little calm, or helped the day loosen its grip, I would be ever so grateful if you liked the video, subscribed, and returned for another slow journey through science made for sleep. It helps this calm corner of the cosmos reach others who may need a gentle place to rest their thoughts. And if you are already half asleep, that is perfectly all right. The galaxies will not be offended. They have been waiting billions of years. They can wait until morning. For now, let the numbers fade. Let the light years become simply distance. Let the galaxies become soft islands of stars far beyond any road we can travel. Let the dark between them become not emptiness, but space enough for wonder. You do not need to imagine all of it. You only need to know that it is there, immense and quiet, while you are here, breathing slowly, held for this moment by a small planet beneath you, a galaxy around you, and a universe wider than thought carrying on without hurry. Sleep well, fellow traveller, wherever you are in this little corner of the Milky Way.